Before we begin, take a moment to settle in. Let your breathing slow. The story we're about to follow takes place in one of the most extreme environments on Earth, a place where the air is thin, the cold is absolute, and sleep becomes something entirely different from what we know. This is not a tale of conquest or drama. It is simply the story of how human beings rest in a landscape designed to resist all human presence. It is a single night, from sunset to the deep middle hours, on the highest mountain in the world. The Indifferent Landscape. The south col of Mount Everest sits at nearly 8,000 metres above sea level. In the language of measurement more familiar to some, that is over 26,000 feet. It is a windswept plateau, a saddle of rock and ice pressed between the summit pyramid of Everest itself and the steep face of Lhotse, the world's fourth highest peak. There are no trees here. There is no vegetation of any kind. There is no soil, no running water, no insects, no birds. The South Col is a place stripped to its most essential elements: stone, frozen water and air. When the sun begins its descent toward the western horizon, the transformation is not gradual. It does not fade gently as it might in a temperate valley or along a coastal plain. The sunset at 8,000 metres is abrupt, almost mechanical. The thin atmosphere that surrounds this plateau holds very little warmth during the day, and it retains none of it when the light goes. The temperature, which may hover around negative 15 degrees Celsius in the late afternoon, begins to fall with a shocking speed. Within minutes of the sun disappearing behind the ridgeline, the air temperature drops to negative 30 degrees Celsius. As full darkness settles, it continues to fall, reaching negative 40 degrees Celsius. Temperature that by coincidence is also negative 40 degrees Fahrenheit. The two scales meet at this point. A strange convergence in a place of extremes. This cold is not merely the absence of warmth. It is an active, penetrating presence. Metal tools left exposed on the coal become brittle and can snap under stress. A piece of rope, flexible in the afternoon, becomes stiff and uncooperative. Exposed human skin, unprotected for more than 60 seconds, begins to freeze solid. The moisture in the outer layers of the skin crystallizes, and frostbite begins its quiet, destructive work. This is not a landscape that tolerates carelessness, but the cold, severe as it is not the defining characteristic of this place. The defining characteristic is the air itself. At 8,000 metres, the atmosphere is so thin that it contains only 1/3 of the oxygen molecules present at sea level. For every breath a person takes here, they receive only 1/3 of the oxygen they would receive standing on a beach or in a city park. This scarcity has profound consequences. The human body, evolved over hundreds of thousands of years to function at or near sea level, cannot adapt to this environment. It cannot regenerate tissue, repair cellular damage, or maintain its normal metabolic processes. At this altitude, the body begins to die. It happens slowly, cell by cell, but it happens. Mountaineers have a name for this zone. They call it the death zone. The term is not metaphorical or dramatic. It is a literal description of a place where human life cannot be sustained indefinitely. Every hour spent here is an hour borrowed from the body's reserves. Every night is a gamble. The South Col is not silent. True silence, the absence of all sound, does not exist here. Instead, there is the wind, the jet stream, a river of fast-moving air that circles the planet at high altitude, occasionally dips low enough to touch the summits of the tallest mountains. When it does, it brings winds of extraordinary violence. These winds can exceed 100 miles per hour. They scour the coal, picking up loose snow and ice particles and hurling them horizontally across the plateau. The sound is a constant, high-pitched shriek, a hissing roar that never stops. It is the sound of the mountain breathing. Scattered across this plateau are the tents of climbers. These are not the large, comfortable shelters one might find at a base camp lower on the mountain. These are small, low-profile geodesic dome tents, engineered to withstand hurricane-force winds. They are made of thin nylon fabric stretched over a lattice of lightweight aluminum poles. The shape is deliberate, rounded, with no flat surfaces for the wind to catch. Even so, the tents shudder and drum constantly in the gale. The fabric snaps and cracks like a whip. Inside, the noise is deafening, a relentless percussion that makes conversation difficult and sleep nearly impossible. And yet, this is where sleep must happen. This is the room. This is the landscape of indifference, a place that neither welcomes nor rejects human presence. It simply exists, cold and thin and loud, waiting for the night to pass, the room with no walls. The tent provides shelter from the wind, but it does not change the fundamental nature of the environment. Inside the thin nylon walls, the air is still brutally cold. A climber's breath, visible as a cloud of vapour, freezes almost instantly on the inside of the tent fabric, forming a layer of frost. If you brush against the tent wall with your sleeping bag, this frost shakes loose and falls like fine snow onto your face and gear. The tent is not a warm refuge. It is simply a barrier against the wind and a marker in the darkness. A small, fragile bubble of human presence in a landscape that has no memory of humanity. The air inside the tent contains the same 1/3 oxygen as the air outside. There is no atmospheric pressure differential, no way to seal the tent and create a breathable environment. The zippers and seams allow constant airflow. The susu, when it is running, consumes oxygen and produces carbon monoxide, which must be vented. The tent is permeable, open to the altitude. The death zone extends to within inches of your face. At 8,000 meters, the human body is in a state of constant physiological crisis. The heart beats faster, trying to circulate the oxygen-poor blood more quickly. The lungs work harder, pulling in breath after breath of thin air. The brain, which consumes roughly 20% of the body's oxygen even at rest, begins to show signs of deprivation. Thinking becomes slower. Decision-making is impaired. Simple tasks, zipping a jacket, lighting a stove, tying a knot, require intense concentration and multiple attempts. This cognitive decline is not imagined. It is measurable. Studies of climbers at extreme altitude have documented significant drops in mental performance, memory, and coordination. The body's response to this oxygen starvation is complex. In the first hours and days at altitude, the body attempts to compensate. It produces more red blood cells, trying to increase the oxygen-carrying capacity of the blood. This process, called acclimatization, is temporary and comes with costs. The increased red blood cell count thickens the blood, making it more viscous. This thick blood is harder for the heart to pump and increases the risk of blood clots, strokes, and other circulatory problems. For lowlanders, people who live most of their lives at or near sea level, this is the inevitable trade-off. More oxygen capacity, but greater cardiovascular strain. But acclimatization is only a partial, temporary solution. It can help a person survive at moderate altitudes, 5,000, 6,000, even 7,000 meters, for weeks or months. But at 8,000 meters in the death zone, acclimatization is not enough. The body cannot sustain itself. It begins to consume its own tissues for energy. Muscle mass is broken down, fat reserves are burned, the immune system weakens, wounds do not heal. Sleep, the body's primary mechanism for repair and regeneration, becomes almost impossible. The soundscape inside the tent is a layered experience. Closest to you is your own breathing, loud, laboured, and irregular. Each breath is deliberate. You can hear the air moving in and out of your lungs, a rasping mechanical sound. Beyond that is the sound of your tent mate, if you have one, breathing in the same strained rhythm. Then there is the constant drumming of the tent fabric in the wind, a noise so persistent that it becomes almost like white noise, a background hum that the mind eventually stops registering consciously. Occasionally, there is the sound of something breaking, a sharp crack in the distance as a tower of ice, collapses somewhere on the mountain, or the metallic clink of a carabiner outside the tent blown against a pole by the wind. There is also, if you listen carefully, the sound of silence beneath the noise. It is not true quiet, but it's a kind of emptiness. This is a place where no life exists, naturally. There are no animals here, no nocturnal insects, no rustling of leaves or grass. The only sounds are those made by the wind, the ice, and the handful of humans who have chosen, for whatever reason, to place themselves here. It is a profound, almost existential kind of quiet. The sound of a landscape that does not care whether you live or die. And in this room with no walls, surrounded by this indifferent cold and thin air, the work of finding rest begins. Who are the Sherpas? The word Sherpa is often misunderstood. In popular usage, particularly in the West, it has become a generic term for a mountain guide or porter, someone who carries loads and assists climbers on expeditions, but this is not what the word means. Sherpa is not a job title, it is the name of an ethnic group, a people with a distinct language, culture and history. The Sherpas call themselves Sherpa, which translates from Tibetan as Eastern People. This name reflects their origins. The Sherpas are not native to the Khumbu Valley of Nepal, the region that surrounds Mount Everest. They came from farther east, from the Kham region of Tibet, an area of high plateaus and remote valleys far from the centres of Tibetan political power. Sometime between 500 and 600 years ago, the exact dates are uncertain as the Sherpa oral tradition does not emphasise precise chronology, these Tibetan Buddhist pastoralists began to migrate. The reasons for this migration are debated by historians. Some suggest it was driven by political instability or local conflicts. Others point to environmental pressures, such as changes in grazing conditions or drought. Still others suggest religious factors, a desire to establish communities in new territories where they could practice their faith with greater autonomy. What is clear is that the migration was deliberate and organised. It was not a panicked flight from immediate danger, but a planned relocation. Families travelled together, bringing their herds of yaks and zhou, a hybrid of yak and domestic cattle, along with their portable possessions. They carried with them the seeds of barley, their staple grain, and the tools of their pastoral life. They also carried their religious texts, prayer wheels, and ritual objects, the material culture of Tibetan Buddhism that would shape their new communities. The journey was arduous. The Sherpas crossed the Himalayan range through high mountain passes. The most famous of these is the Nangpa La, a pass that sits at 5,716 metres above sea level, 18,753 feet. To put this in perspective, this pass is higher than any mountain in the European Alps, higher than any peak in the Rockies, higher than Mount Kilimanjaro. The Nangpa La is not a gentle saddle between peaks. It is a wind-scoured, ice-covered route through some of the most extreme terrain on Earth. The pass was not unknown. It had been used for centuries as a trade route, part of the network of paths that connected Tibet with the kingdoms and valleys to the south. Tibetan traders used it to transport salt, wool and tea down to Nepal, returning with rice, grain and manufactured goods. But crossing it with entire families, with children and elders, with herds of animals, was a different undertaking entirely. The climate at the Nangpa La is severe even in summer. Winter crossings would have been nearly impossible. The migration must have been timed carefully, undertaken during the brief window of relatively stable weather in late spring or early autumn. Even then, the risks were considerable. Storms at this altitude are violent and unpredictable. Avalanches sweep down from the surrounding peaks with little warning. The cold alone is lethal to anyone unprepared or unlucky, but the Sherpas made the crossing successfully. They descended the southern slopes of the Himalaya and entered the Khumbu Valley, a region of steep-sided gorges, hanging glaciers, and high-altitude pastures. The valley is dominated by the presence of three massive peaks: Everest, known in Tibetan as Chomolungma, Mother Goddess of the World, Lhotse, South Peak, and Nuptse Wu, West Peak. These mountains rise more than 8,000 metres above sea level, their summits lost in the jet stream winds, their flanks draped with ice and rock. The Khumbu Valley itself ranges in elevation from about 3,000 metres at its lower reaches to over 5,000 metres at the base of the Great Peaks. This is high by any standard. Most human settlements worldwide are located below 1,500 metres. The Khumbu is a place where altitude is not an occasional challenge, but a constant condition of life. The Sherpas settled in small villages, scattered along the valley's main river systems. Namche Bazaar, positioned at a strategic point where several valleys converge, became the largest settlement and a trading hub. Other villages, Kumjung, Pangboche, Tamer, Photse, were established at various elevations, each with access to grazing land, water, and some measure of protection from avalanches and rockfall. They built their homes from stone, quarried from the abundant rock of the surrounding mountains. The houses are thick-walled, designed to retain heat in the brutal winters when temperatures can drop to negative 20 degrees Celsius or colder. The roofs are flat or gently soaped, sometimes covered with wood and earth, sometimes with stone slabs. Windows are small to minimise heat loss. The interiors are dark, smoky from the cooking fires, but warm. The The Sherpas brought with them their animals, primarily yaks. The yak is perhaps the most important animal in high-altitude Tibet and Nepal. It is a massive, long-haired bovine adapted to extreme cold and thin air. Yaks provide milk, which is made into butter and cheese. They provide meat, though they are slaughtered sparingly because of Buddhist prohibitions against killing. Their hair is woven into fabric and rope. Their dung, dried in the sun, provides fuel for fires in a landscape where wood is scarce. And crucially, yaks are used as pack animals, capable of carrying heavy loads across steep, high-altitude terrain that would be impossible for horses or donkeys. The Sherpas also established terraced fields on the hillsides, wherever the slope was not too steep and the soil was adequate. They grew barley, the only grain that can reliably ripen at these elevations. Barley is hardy, cold-tolerant, and matures quickly, completing its growing cycle in the short summer months when the ground is not frozen. The harvested barley is roasted and ground into flour, which becomes sampa, the staple food of the Sherpa diet. Sampa is mixed with tea or water to form a thick, dough-like paste that is eaten by hand. It is simple, nutritious, and portable, ideal for people whose lives involve long periods spent away from home, tending herds in high pastures or travelling for trade. Buddhism permeates Sherpa culture. The Sherpas practice Tibetan Buddhism, specifically the Nyingma tradition, the oldest school of Tibetan Buddhism. Their religious life is expressed through monasteries, small temples called gompas that are found in or near most villages. These gompas house monks, religious texts, and sacred objects. They are centres of ritual and learning, where festivals are held and where the community gathers for important ceremonies. Prayer flags are ubiquitous in Sherpa villages and along mountain trails. These are rectangular pieces of cloth printed with prayers and mantras, strung on ropes and hung in high places where the wind can blow through them. The flags come in 5 colours: blue, white, red, green and yellow, representing the 5 elements: sky, air, fire, water and earth. As the wind blows, it is believed to carry the prayers outward, spreading blessings across the landscape. Mani stones are another common sight. These are flat rocks carved with the mantra Om Mani Padme Hum, the 6-syllable prayer associated with the bodhisattva of compassion. The stones are placed along trails and around villages, and travellers are expected to pass them on the left, keeping the carved surface on their right as a sign of respect. Over centuries, thousands of these stones accumulate, forming long walls called mani walls that can stretch for hundreds of metres. The Sherpa's religious worldview holds that the mountains are sacred. They are not inanimate objects but living presences, inhabited by gods and spirits. Chomolungma, Mount Everest, is not simply a geographical feature. She is a goddess, a protector, a being deserving of reverence. This belief shapes how Sherpas interact with the mountains. They do not speak of conquering peaks or defeating nature. They speak of asking permission, of showing respect, of moving through the mountains as guests in a sacred space. What is crucial to understand is that the Sherpas did not move to high altitude. They moved from one high altitude region to another. The Kham Plateau, their ancestral homeland, sits at elevations of 4,000 to 5,000 metres. The Nangpa La, the pass they crossed, is at 5,700 metres. The Khumbu Valley, while it contains villages as low as 3,000 metres, extends upwards to the very base of Everest, where base camp sits at 5,364 metres. The Sherpas have never lived at low altitude. For the entire span of their recorded history, they have inhabited elevations where most human beings struggle to function. Children are born at altitude, grow up at altitude, and spend their entire lives at altitude. This is not a matter of acclimatization, the temporary physiological adjustment that lowlanders experience when they visit the mountains. This is multi-generational exposure, the kind of sustained environmental pressure that drives evolutionary adaptation. 5 to 6 centuries, roughly 20 to 25 generations, is a significant span of time in evolutionary terms. It is long enough for genetic adaptations to appear and spread through a population, particularly when the selective pressure is strong. And the selective pressure of high-altitude life is extraordinarily strong. Those individuals whose bodies were slightly better at extracting oxygen from thin air, whose blood flowed slightly more efficiently, whose metabolism was slightly more stable, those individuals had better survival and reproductive outcomes. They were more likely to survive childhood illnesses, more likely to successfully bear and raise children, more likely to live long enough to become grandparents and pass on their knowledge and genes. Over generations, these advantageous traits accumulated. The Sherpa gene pool became increasingly enriched with variants that conferred high-altitude adaptation. This is natural selection operating on a human timescale, visible and measurable. The Sherpas are not superhuman. They are simply human beings whose ancestors survived in a specific environment long enough for their descendants to inherit the physiological tools necessary for that survival. They are, in the most literal sense, adapted to the thin air. This adaptation is not uniform across the population. Like all genetic traits, it varies from individual to individual, but the average Sherpa has a suite of biological characteristics that make them better suited to extreme altitude than virtually any other human population on Earth. These adaptations are now being studied by geneticists, physiologists, and evolutionary biologists who see in the Sherpa people a living example of recent human evolution in action. This biological inheritance, combined with centuries of cultural knowledge about living and working in the mountains, is what allows Sherpas to function at altitudes that would incapacitate most outsiders. It is not courage alone, though they are courageous. It is not training alone, though they are highly skilled. It is the deep integration of biology and culture, of body and knowledge, that has been refined over 25 generations. This is who the Sherpas are. The Eastern people, the children of the high places, the inheritors of the thin air. The first fortress. Skin and fibre. Survival at negative 40 degrees Celsius is fundamentally a problem of heat retention. The human body generates heat through metabolism, the process by which food and oxygen are converted into energy. At rest, an average adult produces roughly 100 watts of heat, equivalent to a standard incandescent light bulb. At high altitude, working hard, carrying loads, climbing steep ice, the body can produce much more, but this heat is constantly being lost to the environment. In the cold, dry air of the South Pole, that heat is stripped away with brutal efficiency. The solution is insulation. The principle is simple. Trap the body's own warmth in layers of material that resist heat transfer. This is not a modern innovation. For as long as humans have lived in cold climates, they have used layered clothing. The Sherpas' ancestors, living on the Tibetan plateau, wore garments made from yak wool, sheepskin, and woven cloth. These materials are still used today in traditional Sherpa clothing, but for work at extreme altitude, they have been largely replaced by synthetic and down-filled fabrics engineered for maximum thermal efficiency. The layering system used by Sherpas on Everest is a carefully designed fortress built from the skin outward. Each layer has a specific function, and the system only works when all layers are present and properly managed. The failure of any single layer can compromise the entire system, allowing cold to penetrate and potentially leading to hypothermia or frostbite. The first layer, worn directly against the skin, is called the base layer. Its primary function is not warmth but moisture management. The human body produces sweat as a cooling mechanism. Even in extreme cold, if you're working hard, climbing, carrying a load, moving quickly, you will sweat. This sweat, if it remains on the skin, becomes a deadly liability. Water is an excellent conductor of heat, and wet skin loses heat 25 times faster than dry skin. In temperatures below freezing, sweat-soaked fabric will freeze, forming a rigid, icy shell against the skin. This is the beginning of hypothermia. Base layers are made from materials that wick moisture. Merino wool and synthetic fibres like polypropylene or polyester are common choices. These fabrics do not absorb water like cotton or silk. Instead, they pull moisture away from the skin through capillary action, the same physical principle that allows water to move up a narrow tube against gravity. The fabric structure consists of fine fibres with small spaces between them. These spaces create channels through which moisture can travel. The moisture is drawn away from the warm, humid surface of the skin and spread across the outer surface of the fabric, where it can evaporate or be transferred to the next layer. The effectiveness of this wicking depends on maintaining a moisture gradient. If the outer layers become saturated, the base layer cannot move moisture away from the skin and the system fails. This is why when a Sherpa arrives at his tent for the night, one of his first priorities is to ensure that his base layer is dry. If it is damp, he will change it if possible. If he has no dry replacement, he will at least remove his outer layers and allow the base layer to air out and dry as much as possible in the tent's cold, dry air. A dry base layer is the foundation of warmth. The base layer covers the entire body, a long-sleeved shirt and long pants, sometimes a one-piece union suit. It fits snugly against the skin without restricting movement. Loose fabric creates air gaps that reduce wicking efficiency and can allow cold air to circulate against the skin. The fabric at the neck, wrists and ankles should fit closely to prevent heat loss through these openings. The second layer, or mid-layer, provides the primary insulation. This is typically a fleece jacket or a light synthetic insulated jacket paired with insulated pants. The principle here is air trapping. These fabrics are constructed with a high loft, a three-dimensional structure that creates thousands of tiny air pockets. Air is a poor conductor of heat, which means it is an excellent insulator. The body's warmth radiates outward from the skin, but instead of passing directly through the fabric and into the cold air, it is caught and held in these air pockets. The temperature inside the mid-layer remains close to body temperature, while the outer surface remains much colder. Fleece is a synthetic fabric made from polyester fibers that are brushed or knitted to create a fuzzy, high-loft texture. It is lightweight, breathable, and retains much of its insulating ability even when damp, significant advantage over natural fibers like wool, which lose insulation when wet. Fleece also dries quickly, which is important in an environment where getting clothing fully dry is difficult. Synthetic insulation, used in some mid-layer jackets, consists of fine polyester fibers arranged in a loose, batting-like structure. These fibers mimic the structure of down, creating air pockets that trap heat. But unlike down, synthetic insulation continues to insulate when wet. This makes it a good choice for layers that might be exposed to moisture from either sweat or snow. Sherpas often wear multiple mid-layers, 2 or even 3 thin fleece jackets rather than one thick one. This allows them to regulate their temperature more precisely. If they are working hard and generating a lot of heat, they can remove one layer. If they stop moving and begin to cool down, they can add it back. This flexibility is critical in an environment where overheating is as dangerous as freezing. Overheating leads to sweating, sweating leads to wet base layers, and wet base layers lead to rapid heat loss once movement stops. The art of layering is knowing when to add or remove layers. Experienced Sherpas make these adjustments constantly throughout the day. Before starting a steep climb, they might remove a mid-layer to prevent overheating. At the top of the climb, when they stop to rest, they immediately put the layer back on to prevent the body from cooling too quickly. This constant management requires attention and discipline, especially when the mind is dulled by altitude and fatigue. The third layer is the shell, and it is the most important single piece of gear. This is the down suit, sometimes called a summit suit or a puffy suit. It is a full-body garment, jacket and pants, filled with high-quality goose down. Down is the layer of fine, fluffy feathers that grows beneath the outer feathers of waterfowl. It is one of nature's most efficient insulators. Down is measured by fill power, a number that describes how much volume a given weight of down will occupy. High-quality expedition down has a fill power of 800 or more. This means that 1 ounce of down will expand to fill 800 cubic inches of space when it is allowed to loft fully. The insulating power of down comes from its structure. Each down cluster consists of a central point from which thousands of tiny filaments radiate outward. These filaments interlock with the filaments from neighbouring clusters, creating a three-dimensional network of air pockets. The air trapped in these pockets is what provides the insulation. The down itself, the protein structure of the feathers, conducts very little heat. It simply holds the air in place. For a given weight, down provides more insulation than any synthetic material. A down jacket that weighs 1 kilogram can provide the same warmth as a synthetic jacket that weighs 2 kilograms. This weight advantage is crucial at extreme altitude, where every gram carried up the mountain represents additional work for oxygen-starved muscles. But down has a critical weakness. It loses all its insulating ability when wet. Water collapses the loft, eliminating the air pockets. Wet down is not just less effective, it is essentially useless as insulation. It also takes a very long time to dry. For this reason, down garments must be protected from moisture at all costs. The outer fabric of the down suit is treated with a water-repellent coating, and the suit is worn only over dry base and mid layers. If the base layer is wet, that moisture will eventually migrate into the down and the suit will fail. The down suit is constructed using a technique called baffling. The outer and inner layers of fabric are stitched together in a series of compartments or baffles that prevent the down from shifting around inside the garment. If the down were allowed to move freely, it would all settle into the lowest parts of the suit due to gravity and compression, leaving cold spots at the shoulders, back, and other areas. Baffling keeps the down evenly distributed. The baffles are typically oriented horizontally on the torso and vertically on the arms and legs to minimize the down's tendency to migrate. High-quality expedition suits use box baffle construction, where vertical walls of fabric separate each baffle, creating true three-dimensional compartments. Cheaper suits use sewn-through construction, where the outer and inner fabrics are stitched directly together. This creates compression lines where the stitching passes through, and these lines become cold spots because there is no insulation where the fabric is compressed. Box baffle construction eliminates these cold spots but is more expensive and slightly heavier. When a Sherpa puts on his down suit, he is essentially wearing a sleeping bag. The suit is thick, bulky, and restricts movement, but it provides warmth that no other garment can match. The jacket extends to mid-thigh and has a hood that can be pulled up over the head. The pants are high-waisted with suspenders to keep them in place, and they overlap with the jacket to prevent any gap where cold could penetrate. The cuffs at the wrists and ankles are elasticized to seal against the skin. The main zipper is covered with a down-filled baffle to prevent heat loss through the metal zipper. At negative 40 degrees Celsius, the down suit is not optional. It is the armour that makes survival possible. Without it, even with all the other layers, the body would lose heat faster than it could produce it. Core temperature would drop, shivering would begin, the body's attempt to generate heat through involuntary muscle contractions. Shivering is inefficient and exhausting. If core temperature continues to drop, shivering stops. This is a dangerous sign. It means the body's heat generation capacity is failing. Consciousness becomes impaired, speech slurs, coordination fails. Without intervention, death follows within hours. But the extremities, the hands, feet and head, require special attention. These are the parts of the body that lose heat most rapidly, and they are the parts most vulnerable to frostbite. When the body is exposed to extreme cold, it prioritizes the survival of the core. Blood flow to the arms and legs is reduced, and the body pulls all available heat inward to protect the heart, lungs, and brain. This is an automatic response called peripheral vasoconstriction. The fingers, toes, nose, and ears are sacrificed. They are expendable from the body's perspective. If they freeze, the person may still survive. If the core freezes, they will not. The hands are protected by a two-layer system. A thin liner glove, made of wool or synthetic fabric, is worn first. This provides a base layer of insulation and also wicks moisture away from the skin of the hands. Over this goes a massive down-filled mitten. Mittens are always used instead of gloves because they allow the fingers to share warmth. Separated fingers, each in their own compartment, lose heat much faster than fingers grouped together in a mitten. The mittens are oversized, almost comical in appearance, but they work. The outer shell of the mittens is made from a windproof, water-resistant fabric. Wind dramatically increases heat loss through a process called convective cooling. Moving air strips away the thin layer of warm air that forms next to the skin, replacing it with cold air. Windproof fabric blocks this air movement, preserving the warm air layer. The mittens also have long gauntlets that extend up the forearms, overlapping with the jacket sleeves to prevent any gap where cold air or snow could enter. Despite these mittens, the hands remain vulnerable. For tasks that require dexterity, operating a stove, adjusting an oxygen regulator, handling a rope, the Sherpa will briefly remove the mittens and work in just the liner gloves. This exposes the hands to the full cold of the environment. The key is speed. Do the task quickly, then get the hands back into the mittens before the cold can penetrate. Even with this caution, the fingertips often become numb. Sensation returns slowly after the mittens are back on, sometimes with an unpleasant tingling or burning feeling as circulation is restored. The feet are protected by a double boot system. The outer boot is a rigid plastic shell designed for climbing. It is stiff enough to support the ankle on uneven terrain and has a sole designed to fit into crampons, metal spikes that are strapped to the bottom of the boot for walking on ice. The outer boot is typically made of injection-moulded plastic, material chosen for its durability and its ability to maintain its shape in extreme cold. Leather boots, which were used in earlier decades, become stiff and brittle at low temperatures. Plastic remains functional. This outer boot provides almost no insulation. It is simply a hard shell. Inside the outer boot is the inner booty, a removable insulated liner. This booty is heavily insulated with closed-cell foam or synthetic batting. Some expedition boots use down insulation in the booty, though this is less common because down loses its insulating properties if it gets wet, and feet, being in contact with snow and ice, are at constant risk of moisture exposure. The inner booty is thick, typically 3 to 5 centimeters of insulation, and soft, unlike the rigid outer shell. It fits snugly around the foot and lower leg, coming up to mid-calf. The booty has its own thin sole, which provides some cushioning and insulation from the cold ground, but the primary protection comes from the thick walls of insulation around the sides and top of the foot. At the end of the day, when a climber arrives at their tent, they remove their boots and separate the inner booties from the outer shells. This is absolutely critical. If the booties are left inside the plastic, outer boots overnight, they will freeze solid. The plastic does not insulate, and the thin air provides no thermal buffering. By morning, the booties will be as hard as wood. Putting them on in that state is nearly impossible. The frozen booty will not flex or conform to the shape of the foot. Even if you manage to force them on, they will cause severe frostbite within minutes because they are colder than the surrounding air and will actively pull heat from your feet. Instead, the booties are brought into the sleeping bag. They are placed at the foot of the bag, or sometimes tucked under the sleeper's armpits, or against the torso, where the body's warmth will keep them pliable. In the morning, the booties are still cold, but they are soft enough to put on. This is one of the many small, methodical acts that make survival possible. It is not dramatic, it is simply necessary. The head is covered by multiple layers. First is a balaclava, a tube of fabric that pulls over the head, covering the scalp, ears, neck, and most of the face. Only the eyes and mouth remain exposed. Balaclavas are typically made from fleece or synthetic fabric, chosen for warmth and moisture wicking. Over the balaclava, a thick insulated hat is worn. This is often a beanie-style cap filled with synthetic insulation or down. The hat covers the top of the head and the ears, which are particularly vulnerable to frostbite. The down suit itself has a hood, which is pulled up over the hat. This hood is heavily insulated and has a wire or stiffener in the front edge, allowing it to be shaped to form a tunnel that shields the face from wind. Some climbers also use a neck gaiter, a tube of fabric that can be pulled up over the nose and mouth for additional protection. The eyes are protected by high-altitude goggles. These are not ordinary sunglasses. They are designed to provide complete coverage, with side shields that block wind and light from entering around the edges. The lenses are dark, filtering out the intense ultraviolet radiation that is much stronger at altitude due to the thinner atmosphere. Snow blindness, a painful condition caused by UV damage to the cornea, can occur within hours of unprotected exposure at high altitude. The goggles prevent this. They also provide physical protection from the wind, which can freeze the surface of the eye if exposed for too long. Even with all this protection, the face remains partially exposed. The nose and the area around the mouth cannot be completely covered because the climber needs to breathe. These exposed areas are highly vulnerable to frostbite. Many climbers develop frostbite on the tip of the nose or on the cheeks despite their best efforts. There is no perfect solution. It is a calculated vulnerability, accepted as part of the cost of being at this altitude. This system, base layer, mid-layer, down suit, and extremity protection, is the first fortress. It is the barrier between the body and the cold. Without it, a person would die within minutes at negative 40 degrees Celsius. With it, they can survive for hours, even overnight, in conditions that would otherwise be immediately lethal. But the system requires constant attention. Zippers must be kept closed. Hoods must be adjusted. Mittens must be kept on except when absolutely necessary to remove them. Layers must be added or removed to prevent sweating. The management of this fortress is a constant vigilant process that never stops, even when exhausted, even when hypoxic, even when the mind is dulled by altitude. It is the work of survival, and it begins the moment the sun sets on the south column of the Extremities, where warmth ends. The human body's response to extreme cold is a process of triage. When core temperature begins to drop, the body does not distribute its limited resources evenly. It makes choices. Blood vessels in the skin and extremities constrict, reducing blood flow to these areas. This is called peripheral vasoconstriction. It is an automatic, involuntary response controlled by the autonomic nervous system. The purpose is simple: keep the vital organs warm at all costs. This response is life-saving in the short term, but it has consequences. The fingers, toes, nose, ears, and cheeks receive less blood. Without adequate blood flow, these tissues cool rapidly. At a certain point, they cool below the freezing point of water, 0 degrees Celsius, 32 degrees Fahrenheit. When this happens, the water inside the cells begins to form ice crystals. These crystals are sharp and rigid. They pierce cell membranes and damage the delicate structures inside the cell. This is frostbite. Frostbite occurs in stages. The first stage, called frost nip, is superficial. The skin turns pale or white and sensation is reduced. If the area is rewarmed gently at this stage, full recovery is possible. The second stage is superficial frostbite. Ice crystals form in the outer layers of skin. The skin becomes hard and frozen, but the deeper tissues remain soft. Blisters may form after a warming. Again, with proper care, most people recover fully, though the affected area may remain sensitive to cold for the rest of their life. The third stage is deep frostbite. Ice crystals form in the muscles, tendons, and bone. The tissue becomes completely frozen, solid and rigid. The skin turns greyish or blue. When deep frostbite is rewarmed, the tissue dies. The body's immune system recognises the dead tissue and begins to break it down. Over days or weeks, the dead tissue turns black and mummified. Eventually it falls off. Fingers, toes, noses, ears, these can all be lost to deep frostbite. For Sherpas working on Everest, the hands are the most critical. They need their hands to tie knots, handle ropes, operate stoves, zip jacket, and perform countless other tasks that require fine motor control. Losing a finger or thumb can end a climbing career. The boots, therefore, are treated with extraordinary care. The double boot system is standard on all high-altitude expeditions. The outer boot, made of rigid plastic, is the structural component. It is stiff enough to support the ankle on uneven terrain and has a sole designed to fit into crampons, metal spikes that are strapped to the bottom of the boot for walking on ice. This outer boot provides no insulation. It is simply a hard shell. Inside the outer boot is the inner booty. This is a soft, thick, insulated sock-like garment. It is usually filled with closed-cell foam or synthetic insulation. Some expedition boots use down insulation in the booty, though this is less common because down loses its insulating properties if it gets wet. The booty is removable. At the end of the day, when a climber arrives at their tent, they take the booties out of the outer shells. This is absolutely critical. If the booties are left inside the plastic outer boots overnight, they will freeze solid. The plastic does not insulate, and the thin air provides no thermal buffering. By morning, the booties will be as hard as wood. Putting them on in that state is nearly impossible, and even if you manage to force them onto your feet, they will cause severe frostbite within minutes because they are colder than the surrounding air and will actively pull heat from your feet. Instead, the booties are brought into the sleeping bag. They are placed at the foot of the bag or sometimes tucked under the sleeper's armpits, where the body's warmth will keep them pliable. This is one of the many small methodical acts that make survival possible. It is not gush and glamorous, it is not dramatic, it is simply necessary. The hands require similar care. The down mittens are essential, but they are also bulky and make detailed work impossible. For tasks that require dexterity, operating a stove, adjusting an oxygen regulator, handling a rope, the Sherpa will briefly remove the mittens and work in just the liner gloves. This exposes the hands to the cold, but only for a few seconds at a time. The key is speed. Do the task quickly, then get the hands back into the mittens before the cold can penetrate. Even with all these precautions, frostbite is common. Minor cases, frostnip on the fingertips or cheeks, are almost expected. More serious cases occur every season. The line between safety and injury is thin, and it is crossed easily through a moment of inattention, a torn glove, a delayed decision. The head too is a major source of heat loss. This is sometimes described by saying that you lose most of your body heat through your head, but this is a misunderstanding. The head is not intrinsically more heat-losing than any other part of the body of the equivalent surface area. The reason so much heat is lost through the head is simply that the head is often the only part of the body left uncovered. In extreme cold, if every other part of your body is insulated but your head is bare, then yes, a disproportionate amount of heat will be lost through the head. The solution is straightforward: cover the head. The balaclava is the primary head covering. It is a tube of fabric that pulls over the head, covering the scalp, ears, neck, and most of the face. Only the eyes and mouth remain exposed. Over this, a thick insulated hat is worn. Some climbers also use a hood, either attached to the down suit or as a separate garment. The goal is to trap warm air around the head and prevent the wind from stripping it away. The face presents a unique challenge. The nose, cheeks, and lips cannot be completely covered because the climber needs to breathe, see, and sometimes eat or drink. These areas are left exposed and are highly vulnerable. High-altitude goggles protect the eyes and the surrounding skin, but the nose and mouth remain at risk. Many climbers develop frostbite on the tip of the nose or the edges of the lips. There is no perfect solution. It's a calculated vulnerability, accepted as part of the cost of being at this altitude. This attention to the extremities, the careful management of gloves, boots, hats and goggles, is a constant, vigilant process. It never stops. Even inside the tent, even while resting, the Sherpa is aware of his hands and feet, checking for numbness, flexing his toes, rubbing his fingers together. Warmth at the extremities is not guaranteed by the gear alone. It must be actively maintained moment by moment, throughout the night. The second fortress, blood and breath. The layering system is essential, but it is not enough. Clothing can trap the body's heat, but it cannot create heat. The body must generate its own warmth through metabolism. And metabolism, at its most basic level, is a process of combustion. The body burns fuel, glucose, fats, proteins, by combining it with oxygen. This chemical reaction releases energy, some of which is used to power muscles and organs, and some of which is released as heat. Without oxygen, this process cannot happen. Without oxygen, the body cannot stay warm. This is where the biological adaptation of the Sherpas becomes critical. At 8,000 meters, the air contains only 1/3 of the oxygen available at sea level. For a lowlander, this scarcity creates a state of constant metabolic crisis. The body is trying to burn fuel, but it does not have enough oxygen to complete the reaction efficiently. It is like trying to run an engine on a lean fuel mixture. The engine sputters, produces less power, and generates incomplete combustion byproducts. In the human body, this incomplete metabolism produces lactic acid, which builds up in the muscles and causes fatigue and pain. It also means the body cannot generate as much heat. But the Sherpa body operates differently. Over 5 to 6 centuries of living at high altitude, the Sherpa population has developed a suite of genetic adaptations that make them significantly more efficient at extracting and using oxygen. These adaptations are not learned behaviors or training effects. They are biological, written into the genome, passed from parent to child. One of the most important adaptations occurs at the cellular level, in the mitochondria. Mitochondria are tiny structures inside nearly every cell in the body. They are often called the powerhouses of the cell because they produce adenosine triphosphate, or ATP, the molecule that stores and transports energy. The process of ATP production requires oxygen. In lowlanders at high altitude, the mitochondria struggle. They do not receive enough oxygen to produce ATP efficiently, so they produce less energy overall, and the cell begins to fail. In Sherpas, the mitochondria are more efficient. Research has shown that Sherpa mitochondria can produce the same amount of ATP using less oxygen than lowlander mitochondria. The mechanism involves the electron transport chain, a series of protein complexes embedded in the inner membrane of the mitochondrion. These complexes pass electrons from one to another in a carefully controlled sequence, and this flow of electrons drives the production of ATP. In Sherpas, these protein complexes appear to operate with less leakage. They waste less energy as heat and channel more energy into ATP production. The result is that Sherpa cells can function at a level of oxygen availability that would cripple a lowlander's cells. This efficiency extends to how the cells handle oxidative stress. When oxygen is scarce, cells sometimes produce reactive oxygen species, unstable molecules that can damage cellular structures. This is a form of internal stress, and the body has mechanisms to neutralize these molecules. Sherpa cells appear to produce fewer reactive oxygen species in the first place than theirs, and they also have more robust antioxidant systems to deal with the ones that do form. This means less cellular damage over time, which is crucial during the prolonged exposure to hypoxia that occurs during multi-day climbs. The genetic basis for some of these adaptations has been identified. One gene in particular, called EPAS1, has received significant attention from researchers. EPAS1 codes for a protein involved in the body's response to low oxygen. This protein is part of a signaling pathway that tells cells how to react when oxygen levels drop. In most human populations, the EPAS1 gene exists in a standard form. But in Tibetans and Sherpas, a different variant of this gene is common. This variant appears to have originated in an ancient human population called the Denisovans, a group that lived in Asia tens of thousands of years ago and interbred with modern humans. The Sherpa variant of EPAS1 seems to moderate the body's response to hypoxia. It prevents the overproduction of red blood cells that occurs in lowlanders, and it may also influence how cells use oxygen at the mitochondrial level. This genetic adaptation is not universal among Sherpas. Like all genetic traits, it varies in frequency across the population, but it is far more common in Sherpa and Tibetan populations than in any other human group. It is a clear signature of evolutionary adaptation to high-altitude life. Another adaptation involves red blood cells. Red blood cells contain hemoglobin, a protein that binds to oxygen in the lungs and carries it to the rest of the body. When a lowlander goes to high altitude, their body detects the low oxygen levels and responds by producing more red blood cells. This is called polycythemia, and it is part of the acclimatization process. The logic is straightforward. If each breath delivers less oxygen, then having more red blood cells to carry that oxygen should help. But this response has a serious drawback. More red blood cells mean thicker blood. The blood becomes more viscous, more like syrup than like water. This thick blood is harder for the heart to pump. It moves more slowly through the blood vessels. The increased viscosity creates greater resistance to flow, which means the heart must generate higher pressure to circulate the blood throughout the body. This increased workload on the heart is exhausting and can lead to heart failure in extreme cases. Thick blood also increases the risk of blood clots. When blood flows slowly and is viscous, the cells and proteins within it have more opportunity to stick together. A clot that forms in a leg vein can break loose and travel to the lungs, causing a pulmonary embolism, potentially fatal blockage of blood flow in the lungs. A clot in the brain can cause a stroke. At extreme altitude, where the body is already under enormous stress, these complications can be lethal. At extreme altitude, many lowland climbers have hematocrit levels, the percentage of blood volume made up of red blood cells, above 55 or 60%. Normal sea level values are around 40 to 45% for men and slightly lower for women. This means lowland climbers at altitude have roughly 20 to 30% more red blood cells than normal. This is dangerously high. Some climbers have hematocrit levels above 65%, which puts them at severe risk for stroke and thrombosis. Sherpas do not have this response. Their red blood cell counts remain relatively normal even at extreme altitude. Their hematocrit levels are typically in the low to mid-40s, only slightly higher than sea level values. This means their blood stays thin and flows easily. The heart does not have to work as hard to circulate it. The risk of clotting is much lower. But how can they deliver enough oxygen to their tissues without extra red blood cells? The answer lies in the blood vessels themselves. Sherpas produce higher levels of nitric oxide, a gas molecule that acts as a signaling compound in the body. Nitric oxide is a simple molecule, just one nitrogen atom and one oxygen atom, but it has profound effects on the cardiovascular system. One of nitric oxide's primary functions is to relax the smooth muscle in the walls of blood vessels. When these muscles relax, the vessels dilate, they become wider. The production of nitric oxide occurs in the endothelium, the thin layer of cells that lines the inside of blood vessels. Specialized enzymes in these cells, called nitric oxide synthases, produce the gas from the amino acid L-arginine. In Sherpas, the activity of these enzymes is elevated, particularly at high altitude. The result is that their blood vessels are in a state of constant mild dilation. Wider blood vessels allow more blood to flow through them, even if the blood itself is not carrying more oxygen per unit volume. This is a matter of fluid dynamics. The flow rate through a tube, or in this case a blood vessel, depends on the diameter of the tube raised to the fourth power. This means that even a small increase in diameter produces a large increase in flow. If a blood vessel dilates by just 20%, the flow through it nearly doubles. This increased flow compensates for the lower oxygen concentration in the blood. The organs and muscles receive the oxygen they need, not because each drop of blood carries more oxygen, but because more blood is flowing through them. The total oxygen delivery, measured as the product of blood flow times oxygen concentration, remains adequate. This adaptation also has a thermal benefit. Blood flow is one of the primary ways the body distributes heat. The heart and the large muscles generate most of the body's warmth, and the blood carries this warmth to the skin and extremities. In lowlanders, the thick blood moves sluggishly, and heat distribution is poor. The core may be warm, but the hands and feet are cold. The body's attempt to conserve heat by constricting peripheral blood vessels, a normal response to cold, is made worse by the increased viscosity of the blood. The result is that the extremities receive very little blood flow and cool rapidly. In Sherpas, the thin blood flows freely, and the nitric oxide-mediated vasodilation partially counteracts the cold-induced vasoconstriction. The vessels remain wider than they would in a lowlander, and more blood reaches the fingers, toes, and other vulnerable areas. Warmth is distributed more evenly throughout the body. This is one of the reasons Sherpas are less susceptible to frostbite than lowland climbers, even when wearing similar gear. Their cardiovascular system is better at delivering warm blood to the areas that need it most. The nitric oxide system also has effects on the lungs. At high altitude, a phenomenon called hypoxic pulmonary vasoconstriction occurs. This is a reflex in which the small blood vessels in the lungs constrict when they detect low oxygen levels. The purpose of this reflex, under normal conditions, is to redirect blood flow away from poorly ventilated parts of the lung and toward better ventilated areas. This improves the efficiency of gas exchange. But at high altitude, where the entire lung is exposed to low oxygen, this reflex causes widespread constriction of the pulmonary blood vessels. The result is increased pressure in the pulmonary circulation. The right side of the heart, which pumps blood through the lungs, must work harder to overcome this increased resistance. In severe cases, the pressure becomes so high that fluid is forced out of the blood vessels and into the lung tissue itself. This is called high-altitude pulmonary edema, or HAPE. It is a life-threatening condition. The lungs fill with fluid, making breathing extremely difficult. Without immediate descent to lower altitude, HAPE can be fatal within hours. Sherpas are much less susceptible to HAPE than lowlanders. The elevated nitric oxide in their systems appears to counteract the hypoxic pulmonary vasoconstriction. The nitric oxide dilates the pulmonary blood vessels, keeping the pressure in the lung circulation lower and reducing the risk of fluid leakage. This protection is not absolute. Sherpas can still develop HAPE, particularly if they ascend too quickly without proper acclimatization, but their baseline risk is much lower. A third adaptation involves breathing. At rest, at sea level, an average adult takes about 12 to 16 breaths per minute. At high altitude, this rate increases. The body tries to compensate for the low oxygen by breathing more frequently. But there is a limit to how much this helps, because the air itself still contains the same low concentration of oxygen. Breathing faster simply moves more low oxygen air through the lungs. It does help somewhat. It maintains a steeper gradient for oxygen diffusion from the lungs into the blood, but it is not a complete solution. The control of breathing is complex. It is regulated by chemoreceptors, specialized cells that monitor the levels of oxygen, carbon dioxide, and pH in the blood. These receptors are located in the carotid arteries in the neck and in the brainstem. When they detect low oxygen or high carbon dioxide, they send signals to the respiratory centers in the brainstem, which increase the rate and depth of breathing. At a high altitude, the balance between these signals shifts. The low oxygen drives an increase in breathing, but the increased breathing causes the body to blow off more carbon dioxide. Lower carbon dioxide levels make the blood more alkaline, which actually inhibits breathing. These two effects, one pushing breathing up, one pushing breathing down, create a kind of oscillation, which is part of what causes the periodic breathing that occurs during sleep. Sherpas, even at rest, breathe faster than lowlanders at the same altitude. Their baseline respiratory rate is higher. This is not because they are out of breath or struggling. It is simply the normal state of their respiratory system. They take more breaths per minute, each breath bringing in a small amount of oxygen, and the cumulative effect is a more stable oxygen supply to the blood. Research has shown that the chemoreceptors in Sherpas are more sensitive to low oxygen levels. They respond more quickly and more strongly when oxygen drops. This heightened sensitivity means that the Sherpa body is constantly making small rapid adjustments to breathing rate to maintain optimal oxygen levels. It is a finely tuned system honed over generations. There is also evidence that Sherpas have larger lung volumes relative to their body size. The lungs are not just bigger, they have more surface area for gas exchange. The alveoli, the tiny air sacs where oxygen moves from the air into the blood, are more numerous or more densely packed. This increased surface area allows for more efficient oxygen uptake. Each breath may not contain more oxygen, but more of that oxygen is transferred into the blood. The diaphragm, the primary muscle of breathing, also appears to be stronger in Sherpas. Breathing at high altitude is hard work. The lungs are expanding and contracting 30 to 40 times per minute, sometimes more. The diaphragm must generate the force to pull air into the lungs against the reduced atmospheric pressure. A stronger diaphragm can sustain this work for longer periods without fatiguing. These three adaptations, mitochondrial efficiency, cardiovascular optimization through nitric oxide and controlled red blood cell production, and enhanced respiratory function, work together to create a state of relative metabolic stability. A Sherpa at 8,000 meters is not comfortable, but his body is not in a state of panic. His cells are receiving enough oxygen to function. His heart is not straining to pump thick blood. His brain is not fogged by severe hypoxia. He is in a baseline state of function that allows him to work, to move, and crucially to rest. This biological fortress is the second layer of protection against the cold and the altitude. The first fortress, the clothing, traps the heat the body produces. The second fortress, the adapted physiology, ensures that the body can actually produce that heat in an environment where most human bodies cannot. Without this adaptation, all the downsuits and sleeping bags in the world would not be enough. The body would be unable to generate the metabolic warmth needed to stay alive. The cold would win, but with this adaptation, survival becomes possible. Not easy, not comfortable, but possible. The Sherpa body, shaped by 5 centuries of living in the thin air, has the tools it needs to function at the edge of the death zone. It is a quiet biological miracle, written in genes and expressed in every breath, every heartbeat, every cell working efficiently in an environment that should be impossible for human life. This is the foundation. This is what makes everything else, the tent, the sleeping bag, the oxygen, the communal warmth, sufficient. Without this biological adaptation, no amount of technology or willpower would allow a person to rest at 8,000 meters. But with it, rest becomes achievable. And rest, however fragmented and inadequate, is what allows the climb to continue. Entering the tent. The sun has been down for perhaps half an hour. The temperature has dropped below negative 30 degrees Celsius and is still falling. The wind is a steady, roaring presence, gusting to perhaps 80 or 90 miles per hour. A Sherpa climber, returning from a day of carrying loads or fixing ropes on the Lhotse face, approaches his tent. It is one of several scattered across the South Col, each a small dome of yellow or orange nylon, vibrating violently in the wind. He is exhausted. The work of climbing at this altitude is metabolically extreme. Even simple tasks, walking, lifting, bending, require immense effort. His legs are heavy, his chest aches from the constant laboured breathing. His throat is dry and raw. He has been breathing hard all day, and the dry, cold air has stripped all moisture from his mouth and airways. He is deeply thirsty, but there is no water here. There is only ice and snow, and that will have to be melted. He reaches the tent and unzips the entrance. Inside, his tent mate is already present, sitting in his sleeping bag, waiting. They greet each other with a nod or a few words. Conversation is difficult. The altitude makes speech feel like an effort, and the wind noise is so loud that shouting is required to be heard. They speak only when necessary. The Sherpa removes his crampons, the metal spikes strapped to his boots, and places them outside the tent. He brushes the snow and ice from his downsuit and then crawls inside, zipping the entrance shut behind him. The wind noise does not decrease. It is still deafening, but at least the wind itself is stopped. The tent interior feels fractionally warmer, perhaps -20 degrees instead of -40. This small difference is significant. He begins the process of adjusting his layers. He's still wearing his full-down suit, the jacket and the insulated pants. This suit is necessary when moving outside, but inside the tent it is too warm. This may seem counterintuitive. How can anything be too warm at -20 degrees? But the human body is a heat engine, and if it is wrapped in too much insulation, while it is still generating metabolic heat from the day's exertion, it will begin to sweat. And sweat, as we have discussed, is the enemy. He unzips the down suit and carefully removes it, folding it and placing it at the foot of his sleeping bag. He's now wearing his mid-layers, a fleece jacket, insulated pants, and his base layers beneath those. This is the configuration he will maintain for the rest of the evening. He keeps his hat on. His feet remain inside the inner booties of his double boots, though he has removed the outer plastic shells and placed them outside the tent. The tent is small. It is a 4-season, high-altitude geodesic dome, designed to be lightweight and wind-resistant. The interior is perhaps 7 feet in diameter and 4 feet tall at the highest point. There is no room to stand. Everything is done sitting or lying down. The floor is covered with foam sleeping pads which provide insulation from the frozen ground. The walls are thin nylon, coated with frost on the inside. Gear is scattered everywhere: ropes, harnesses, oxygen cylinders, water bottles, food bags. There is no organisation, only functional chaos. His tent mate has already begun the evening's work. In the centre of the tent, a small stove is set up. It is a high-altitude canister stove, a marvel of engineering designed to function in conditions where most combustion devices fail. At 8,000 metres, the air pressure is so low that water boils at 71 degrees Celsius instead of the usual 100 degrees. Fuel does not vaporise properly. Flames are weak and unstable. This stove is designed to compensate for all of these problems. It has a pressurised fuel canister and a burner assembly that preheats the fuel before it reaches the flame. It is loud, a high hissing roar, but it works. On top of the stove is a pot, and in the pot is a mixture of snow and ice. The first task of the evening has begun: making water. The work of water. Water is life. This is a truism, repeated so often that it has lost its impact. But at 8,000 metres in the death zone, it is not a metaphor. It is a plain, urgent fact. Without water, a person will die here in a matter of days, perhaps hours. Dehydration is one of the primary killers at extreme altitude. The problem is that there is no liquid water. The temperature is far below freezing. There are no streams, no springs, no melting snow except that which is deliberately heated. Every drop of water a climber consumes must be produced manually by melting snow and ice over a stove. This process is slow, laborious, and absolutely essential. Dehydration at altitude occurs for several reasons. The first is the breathing rate. A climber at 8,000 metres is taking perhaps 30 to 40 breaths per minute, sometimes more. Each breath is an exhalation of the moist air. The lungs humidify the air as it passes through the respiratory tract, and that moisture is lost to the environment. Over the course of a day, this adds up to litres of water lost through respiration alone. The physiology of this moisture loss is straightforward but relentless. The air passages in the nose, throat and lungs are lined with mucous membranes. These membranes are kept moist by glands that continuously secrete fluid. This moisture serves several purposes. It traps dust and particles, it helps regulate temperature, and it facilitates the movement of oxygen across the thin barrier between air and blood in the alveoli. But this moisture must come from somewhere, and that somewhere is the body's total water supply. At sea level, in a temperate climate, a person loses perhaps 300 to 400 millilitres of water per day through respiration. This is a small amount easily replaced by normal drinking and eating, but at 8,000 metres, the breathing rate is 3 to 4 times higher than at sea level. Simple mathematics reveals the scale of the problem. 3 to 4 times the breathing rate means 3 to 4 times the respiratory water loss. A climber at extreme altitude can lose more than a litre of water per day just through breathing. The second reason is the dryness of the air. At high altitude, the air contains very little water vapour. Relative humidity is often near zero. This extremely dry air pulls moisture from any surface it contacts: skin, lips, the inside of the nose and throat. The mucous membranes dry out and crack. The skin becomes desiccated. This passive moisture loss is constant and unavoidable. The physics of this process involves vapor pressure gradients. Water molecules naturally move from areas of high concentration to areas of low concentration. The moist surfaces inside the body represent areas of high water vapor concentration. The surrounding air, with its near zero humidity, represents an area of low concentration. The gradient between these two states is steep, and water molecules flow rapidly from the body into the air. This is evaporation, and it happens continuously. The air at high altitude is dry for a simple reason. Cold air cannot hold much water vapor. The capacity of air to contain moisture depends on temperature. Warm air can hold a great deal of water vapor. This is why tropical regions feel humid. Cold air can hold very little. At negative 40 degrees Celsius, the air's capacity to hold moisture is extremely low. Any water vapor that does enter the air quickly condenses or freezes out as ice crystals. The result is air that is not just cold but profoundly dry. This dry air affects more than just thirst. The cracking of mucous membranes in the nose and throat creates open wounds. These wounds are painful and can become infected, though at this altitude the cold tends to inhibit bacterial growth. More significantly, the damaged membranes bleed easily. Many climbers experience nosebleeds at high altitude, sometimes severe enough to be alarming. The blood loss is rarely dangerous in itself, but it represents additional fluid loss from an already dehydrated body. The lips are particularly vulnerable. Without the protective layer of moisture, they crack and split. The cracks can be deep enough to bleed. Chapstick and lip balm help, but they are only partially effective. Many climbers return from high-altitude expeditions with severely damaged lips that take weeks to heal. The third reason is that the body's thirst mechanism does not function properly at altitude. Under normal conditions, the sensation of thirst is triggered by receptors that detect changes in blood osmolality, the concentration of dissolved substances in the blood. When the blood becomes too concentrated, these receptors signal the brain, and the person feels thirsty and drinks water. But at high altitude, for reasons that are not fully understood, this mechanism becomes blunted. Climbers do not feel thirsty even when they are severely dehydrated. They must force themselves to drink even when they have no desire to. The mechanism behind this blunted thirst response may involve the hormonal changes that occur at altitude. The body produces more of a hormone called atrial natriuretic peptide, or HANEP, which causes the kidneys to excrete more salt and water. This is part of the acclimatization process. The body is trying to reduce blood volume to compensate for the thicker blood caused by increased red blood cell production. But the increased ANP also suppresses the sensation of thirst. The body is telling itself to get rid of water even when water is desperately needed. Dehydration has serious consequences. When the body loses water, the blood volume decreases. The blood becomes thicker and more viscous. This is on top of the increased red blood cell count that lowlanders experience during acclimatization, so the effect is compounded. Thick blood is harder to pump, which strains the heart. It flows more slowly through the capillaries, which reduces oxygen delivery to tissues. It is more prone to clotting, which increases the risk of stroke, pulmonary embolism, and deep vein thrombosis. The cardiovascular strain of dehydration is measurable. Heart rate increases as the heart tries to compensate for the reduced blood volume by beating faster. Blood pressure can become unstable, sometimes elevated due to the increased blood viscosity, sometimes low due to the reduced volume. The heart muscle itself, working harder and receiving less oxygen, becomes fatigued. In extreme cases, this can lead to arrhythmias, irregular heartbeats that can be fatal. Dehydration also impairs cognitive function. The brain is highly sensitive to changes in blood chemistry. Even mild dehydration can cause difficulty concentrating, slowed reaction times, and poor decision-making. At extreme altitude, where cognitive function is already impaired by hypoxia, dehydration makes things much worse. A dehydrated climber is more likely to make a fatal mistake, misjudging a route, forgetting to clip into a rope, failing to recognize the signs of frostbite or altitude sickness. Research has documented the cognitive effects of combined hypoxia and dehydration. Simple tests of memory, attention, and reasoning show significant impairment. Reaction times slow by hundreds of milliseconds. The ability to perform mental arithmetic deteriorates. Judgment becomes clouded. These deficits are dangerous in an environment where a single mistake can be fatal. Finally, dehydration increases the risk of frostbite. Blood flow to the extremities is already reduced by the cold. If the blood is also thick and sluggish, the fingers and toes receive even less circulation. The tissues cool more rapidly, and frostbite sets in faster. Well-hydrated blood flows more easily and delivers more warmth to the vulnerable extremities. This is one of the most important but least appreciated protective factors against frostbite. For all these reasons, hydration is a top priority. Experienced climbers and Sherpas aim to drink 4 to 6 litres of water per day at high altitude. This is an enormous amount, far more than most people drink at sea level, but it is necessary. The challenge is producing this water. Making this water is the first major task of the evening. The tent mate has filled the pot with chunks of snow and ice scavenged from around the tent. The stove is roaring beneath it, and slowly, over the course of 20 to 30 minutes, the snow begins to melt. It does not melt into clear water immediately. First it compacts down into a dense, slushy mass. Then gradually it liquefies. The process is maddeningly slow. A full pot of snow might yield only a third of a pot of water. The physics of melting snow at high altitude is more complex than it appears. At sea level, water boils at 100 degrees Celsius. This is the temperature at which the vapour pressure of the water equals the atmospheric pressure, and bubbles of water vapour can form throughout the liquid. But atmospheric pressure at 8,000 metres is only about 1/3 of sea level pressure. At this reduced pressure, water boils at approximately 71 degrees Celsius. This lower boiling point has several consequences. First, it means that water heated to the boiling point is not as hot as boiling water at sea level. This cooler water is less effective at warming the body when drunk, and it is less effective at rehydrating freeze-dried food. Second, the lower boiling point means that less heat energy is required to bring water to a boil, but the reduced atmospheric pressure also means that the stove flame is weaker and less efficient. These two effects partially counteract each other, but the net result is that melting snow and boiling water at altitude takes longer than at sea level. The stove itself is a marvel of engineering. High-altitude stoves must function in conditions where combustion is difficult. Fire requires 3 things: fuel, oxygen, and heat. At 8,000 metres, the oxygen concentration is only 1/3 of sea level. This makes combustion inefficient. Flames are weak and unstable. Many types of stoves that work perfectly at sea level will not ignite at all at extreme altitude. The stoves used by Sherpas and climbers on Everest are typically canister stoves. These use pressurized canisters of liquefied petroleum gas, a mixture of propane and butane. The canister itself is a small lightweight metal cylinder, threaded to attach to the stove burner. Inside the canister, the fuel is stored as a liquid under pressure. When the valve is opened, the pressure drops, and the liquid evaporates into a gas that flows to the burner. But at extreme cold, this evaporation process slows down or stops entirely. Butane, one of the primary components of the fuel mix, will not vaporize below -1 degree Celsius. Propane continues to vaporize down to much lower temperatures, but even propane's evaporation rate is significantly reduced at -40 degrees. To solve this problem, high-altitude stoves use a liquid feed system. Instead of relying on the fuel to evaporate inside the canister, the stove draws liquid fuel out of the canister and vaporizes it in a preheater tube that is heated by the flame itself. This creates a self-sustaining cycle. The flame heats the fuel, which vaporizes and feeds the flame. The sound of the stove is distinctive, a high, pressurized hiss, overlaid with the deeper roar of combustion. It is loud, particularly in the confined space of the tent, but the sound is comforting. It is a sound of work, of life, of human presence. In the endless howling of the wind outside, the stove's roar is a small, defiant counterpoint. The process of melting snow is also inefficient from a thermodynamic perspective. Snow has a very low thermal conductivity, which means heat does not transfer through it easily. When you place a pot of snow on a stove, the snow at the bottom melts first, but the snow above it acts as insulation, slowing the transfer of heat. You must constantly stir the snow, breaking up the insulating layer and bringing new snow down into contact with the hot bottom of the pot. This stirring is part of the ritual, methodical task performed with a spoon or a small stick. Once the first batch of water is ready, it is poured into insulated thermoses. These are wide-mouthed bottles with thick foam or vacuum insulation. The goal is to keep the water from freezing overnight. If the water is allowed to cool to the ambient temperature of the tent, it will freeze solid within an hour. The thermoses prevent this, though even they are not perfect. By morning, the water will be cold, but it should still be liquid. The insulation in these bottles works by creating a barrier to heat transfer. Foam insulation contains thousands of tiny air pockets, and air is a poor conductor of heat. Vacuum insulation is even more effective. It uses a double-walled bottle with the space between the walls evacuated of air. Since there is no air in the gap, there is no medium through which heat can be conducted or convected. Heat can only escape through radiation, which is a much slower process. A good vacuum bottle can keep water from freezing for 12 to 24 hours at extreme altitude. The process is repeated. More snow is added to the pot, more waiting, more melting. The two Sherpas take turns managing the stove, feeding it fuel canisters, adjusting the flame, stirring the snow. They do not rush. There is no point in rushing. This is simply how long it takes. A typical evening's work, producing enough water for drinking, cooking, and filling the morning thermoses, can take 2 to 3 hours. During this time, they drink. They force themselves to consume water even though they do not feel thirsty. The water is lukewarm when it first comes off the stove, but it cools quickly in the cold air. It is not pleasant to drink. Tepid water when you are cold is never appealing, but it is necessary. They drink until their stomachs feel bloated and uncomfortable. This is the goal. Only by drinking past the point of comfort can they ensure they are adequately hydrated. Some Sherpas add flavour to the water. Tea, bouillon, powdered juice mix. This makes the drinking slightly more tolerable. Tea is particularly popular. It provides not only hydration, but also warmth and a small amount of caffeine, which can help with alertness and may slightly ease the altitude headaches that almost everyone experiences. Black tea is common, as is the traditional Tibetan butter tea, though making authentic butter tea at high altitude is difficult and time-consuming, so it is usually reserved for lower camps. The melting continues. Steam rises from the pot, adding a tiny amount of moisture to the dry air inside the tent. This moisture immediately freezes on the tent walls, adding to the layer of frost that coats the interior. The frost layer grows thicker throughout the night, and by morning the inside of the tent looks like the inside of a freezer, every surface white and crystalline. After perhaps 2 hours, enough water has been made. The thermoses are full. The Sherpas drink some of the water immediately, forcing themselves to keep drinking even though they do not feel thirsty. The remaining water is used to prepare food. This is the next task, and it too requires time and patience. Fueling the internal furnace. Eating at altitude is a chore. There is no other word for it. The appetite, like the thirst mechanism, is suppressed by the hypoxia. Food tastes bland, unappealing. The act of chewing and swallowing requires effort. The stomach feels uneasy, sometimes nauseous. Many climbers report that they have to force themselves to eat at high camps, that the thought of food makes them feel vaguely ill. But eating is not optional. The body is burning an extraordinary number of calories. At sea level, at rest, an average adult burns roughly 2,000 calories per day. At 8,000 meters, just maintaining basic metabolic functions, keeping the heart beating, the lungs breathing, the body warm, requires 5,000 to 6,000 calories per day. If the person is also moving, working, climbing, the number can rise to 8,000 or even 10,000 calories. This metabolic demand is driven by 2 factors. The first is the cold. The body must generate heat to maintain core temperature. This heat is produced by metabolic combustion, which requires fuel. The colder the environment, the more fuel is needed. The second factor is the altitude. The body is working harder to do everything. The heart is beating faster. The lungs are breathing faster. The muscles are working at a lower efficiency because they are not receiving enough oxygen. All of this requires energy, and energy comes from food. If a climber does not eat enough, the body will begin to consume its own tissues. First, it will burn through glycogen, the stored form of glucose found in the liver and muscles. This runs out quickly, usually within a day. Next, it will burn fat. Fat is an excellent energy source, and most people have enough fat stores to last for weeks. But burning fat alone is not enough to sustain the body at extreme altitude. The process of fat metabolism is slow and it requires oxygen. In the death zone, where oxygen is scarce, fat metabolism is inefficient. Eventually, the body will begin to break down muscle tissue. This is called catabolism, and is a sign of severe energy deficit. Muscle protein is converted into glucose through a complex biochemical pathway. This glucose can be used for energy, but at a terrible cost. The muscles become weaker, the body loses strength and endurance. Climbers who spend too long at extreme altitude without adequate food often lose significant amounts of muscle mass. They return from expeditions visibly thinner, their faces gaunt, their limbs stick-like. The food available at high camps is limited. Fresh food is impossible. Anything with significant water content will freeze. Climbers and Sherpas rely on freeze-dried meals, energy bars, chocolate, nuts, and dried fruit. These are calorie-dense, lightweight, and do not spoil. Freeze-dried meals are the most common dinner option. They come in foil pouches and are designed to be rehydrated with boiling water. The Sherpa pours some of the hot water from the pot into the pouch, seals it, and waits for 10 minutes while the food rehydrates. The meal might be a curry, a pasta dish, or a rice bowl. The flavour is acceptable but not particularly good. At altitude, this does not matter, because everything tastes muted anyway. The important thing is the calories. A typical freeze-dried meal contains 600 to 800 calories. This is not enough. The Sherpas will often eat 2 meals, plus several energy bars, plus chocolate and nuts. They are trying to take in as many calories as possible, knowing that tomorrow will demand even more. Some Sherpas bring traditional foods from home. Tsampa, roasted barley flour, is a staple of Tibetan and Sherpa diets. It is eaten by mixing the flour with tea or water to form a thick dough-like paste. It is high in carbohydrates and has a mild, nutty flavour. It is comfort food, a taste of home in this alien landscape. It is not particularly calorie-dense compared to chocolate or energy bars, but it is familiar. And familiarity has value. The act of eating is methodical. The Sherpas do not enjoy the meal. They are not savouring the flavours or relishing the experience. They are simply consuming fuel. They chew slowly, swallow deliberately, and force themselves to take another bite. It is work, like melting the snow, like setting up the tent, like climbing. It is another task in the long list of tasks required to survive, the night. After the meal, the stove is turned off. The sudden silence is jarring. The roar of the stove has been a constant background noise for the past 2 or 3 hours, and its absence leaves a void. Now there is only the wind, the flapping of the tent fabric, and the sound of breathing. The Sherpas begin the final preparations for sleep. Building the inner sanctuary. The sleeping bag is the innermost layer of the fortress, the final barrier between the human body and the cold. It is also the most critical piece of survival gear. A person can survive a night at 8,000 meters without a down suit if they are moving constantly and generating heat through exertion. But they cannot survive a night without a sleeping bag. Once the body stops moving and metabolic heat production drops to resting levels, the cold will penetrate any amount of clothing within hours. The sleeping bag is not optional. Expedition-grade sleeping bags designed for use in the death zone are engineering marvels. They are rated to negative 40 degrees Celsius, sometimes colder. They are filled with the highest quality goose down available, typically 800 fill power or higher. The down is distributed and subtracted in a series of baffles, just like the down suit, to prevent shifting and cold spots. The bag is shaped like a mummy, tapering from the shoulders down to the feet, which minimises the interior volume. Less interior space means less air for the body to heat, which means more efficient warmth retention. The bag has several features designed specifically for extreme cold. The hood cinches tightly around the face, leaving only a small opening for the mouth and nose. This prevents warm air from escaping out the top of the bag. There is a thick insulated collar, called a draft collar, around the neck and shoulders. This collar is essentially a separate tube of down-filled fabric that sits inside the main body of the bag. Its purpose is to block any airflow between the interior of the bag and the outside world. Even with the hood cinched tight, there are small gaps around the face. The draft collar seals these gaps. The zipper, which runs along the side of the bag, is another potential weak point. Zippers are made of metal or plastic, neither of which insulates. A zipper creates a line of thermal conductivity straight through the insulation. To counteract this, expedition bags have a baffle. a tube of insulated fabric that runs along the inside of the zipper. This baffle covers the zipper and prevents heat loss through the metal. Before getting into the bag, the Sherpas prepare the sleeping platform. The tent floor is made of nylon fabric. Beneath that is the frozen ground of the South Pole, solid ice and rock at -40 degrees. Without insulation between the sleeper and the ground, body heat would be conducted directly into the ice. The sleeper would lose heat from below faster than the sleeping bag could replace it from above. This is called conductive heat loss, and it is one of the most dangerous and underestimated threats in cold weather camping. The solution is a sleeping pad. This is a foam or inflatable mat, roughly 6 feet long and 2 feet wide, that lies on the tent floor. The pad is made of closed-cell foam, which means it consists of thousands of tiny sealed air bubbles. Air is an excellent insulator, and the foam prevents heat from being conducted downward into the ground. The pad is typically 2 to 3 inches thick. It is not soft or comfortable. It is firm, almost rigid, but comfort is not the purpose. The purpose is insulation. Once the pad is in place, the Sherpa unrolls his sleeping bag on top of it. He then begins to prepare the items that will go inside the bag with him. This is a critical step. Certain pieces of gear must be kept warm or they will become unusable. Certain items are needed during the night and must be within reach. The first items are the inner booties from the double boots. These are removed from the outer plastic shells and placed at the foot of the sleeping bag. If the booties are left outside the bag, they will freeze solid. In the morning, they will be impossible to put on. Even if you manage to force them onto your feet, they will be so cold that they will cause immediate frostbite. By keeping the booties inside the sleeping bag, they remain pliable and warm, or at least not dangerously cold. Next to the water bottles, if left outside the sleeping bag, the water will freeze. Frozen water is useless. The Sherpa needs to be able to drink during the night. At altitude, the body continues to lose moisture through respiration even while sleeping. Waking up dehydrated is dangerous and unpleasant. The water bottles, typically 2 or 3 insulated thermoses, are placed inside the bag, often near the torso or tucked into the sides. Batteries are also brought into the bag. At extreme cold, batteries lose their charge rapidly. A headlamp with fresh batteries might work for 20 minutes outside the tent, then die. The batteries are not actually dead. They're just too cold to function. Warming them up restores their function. Headlamps and radios are essential as safety equipment. Their batteries are kept inside the sleeping bag, usually in a small stuff sack or the pocket. Some climbers also bring their oxygen regulator inside the bag. The regulator is the device that controls the flow of oxygen from the cylinder to the mask. It has small moving parts and rubber seals. At extreme cold, these can freeze or become brittle. A malfunctioning regulator can mean no oxygen, which can mean death. Not all climbers do this. Some prefer to keep the regulator attached to the oxygen cylinder outside the bag, but it is a judgment call. Once all the items are staged, the Sherpa gets into the bag. He's still wearing his base layers and mid layers. This may seem unnecessary. Why wear clothes inside a sleeping bag? But at -40 degrees, the sleeping bag alone is not enough. The bag is rated to -40, but this rating assumes the person inside is wearing some insulation. A naked person in a -40 bag would still be dangerously cold. He wriggles down into the bag, feet first, pulling the down-filled fabric up around his body. He positions the inner booties at his feet, the water bottles at his sides. He cinches the hood tight around his face, pulling the drawstrings until only a small oval opening remains around his nose and mouth. He pulls the draft collar snug around his neck. He adjusts his position, making sure there are no gaps where cold air can seep in. The sleeping bag is now a sealed cocoon. Inside, the temperature begins to rise. It will not become warm. That is too much to expect, but it will stabilize at perhaps -5 to -10 degrees Celsius, depending on how much body heat he can generate. This is cold enough that most people at sea level would be uncomfortable. But at 8,000 meters, after a day of hard work, it feels almost warm by comparison. He is ready to attempt sleep. The liminal state begins. He closes his eyes. His body is exhausted. His muscles ache from the day's work. His lungs are tired from the constant laboured breathing. His mind is fogged by the hypoxia. Every part of him wants to sleep. But sleep does not come easily. At sea level, sleep is a relatively smooth transition. The brain passes through stages of progressively deeper unconsciousness, light sleep, deep sleep, REM sleep, in a predictable cycle. The body relaxes, the heart rate slows, breathing becomes regular and shallow, the brain consolidates memories, repairs tissues, and performs the maintenance work that can only happen when we are not awake. But at 8,000 meters, sleep is not like this. The brain, sensing the dangerously low oxygen levels, fights to stay awake. It is terrified of shutting down in an environment where unconsciousness could mean death. This conflict between the body's need for rest and the brain's survival instinct creates a disturbed, fragmented state that is neither fully awake nor fully asleep. The primary manifestation of this conflict is a phenomenon called periodic breathing, or Cheyne-Stokes respiration. It is a cyclic pattern of breathing that occurs in nearly everyone who sleeps at extreme altitude. The cycle is predictable, repeatable, and deeply disturbing to experience. The cycle begins as the person drifts into a light sleep. As they do, their breathing begins to slow and becomes less deliberate. This is normal. During sleep, the body's autonomic nervous system takes over control of breathing, and the rate and depth of each breath are regulated automatically based on the levels of oxygen and carbon dioxide in the blood. The regulation of breathing is controlled by chemoreceptors, specialized nerve cells located in the carotid arteries in the neck and in the brainstem. These receptors constantly monitor the chemical composition of the blood. There are two primary signals they track: oxygen levels and carbon dioxide levels. When oxygen drops or carbon dioxide rises, the receptors send signals to the respiratory centers in the brainstem, which increase the rate and depth of breathing. When oxygen rises or carbon dioxide drops, the signals decrease and breathing slows. At sea level, this system maintains remarkably stable blood chemistry. Oxygen saturation typically stays between 95 and 100%. Carbon dioxide levels remain within a narrow range. The system is finely tuned, with multiple feedback loops that prevent wild swings in either direction. But at high altitude, the system becomes unstable. The fundamental problem is that the oxygen levels are already dangerously low. At 8,000 meters, even a person who's awake and breathing normally has an oxygen saturation of only 70 to 80%, compared to 95 to 100% at sea level. This leaves very little margin for error. As the sleeping person's breathing slows, the oxygen level in the blood drops even further. After just a few breaths, the oxygen saturation can fall from 75% to 65%. The brain's oxygen sensors detect this drop. They send an urgent signal: breathe more. The sleeping person's breathing suddenly becomes rapid and deep. They hyperventilate, taking in as much air as possible. Each breath is large, pulling the maximum volume of thin air into the lungs. This rapid breathing raises the oxygen level in the blood. Within 30 seconds to a minute, the oxygen saturation climbs back up to 75 or 80%. Crisis averted, it would seem, but the hyperventilation has created a new problem. By breathing so rapidly and deeply, the person has blown off too much carbon dioxide. Carbon dioxide is not just a waste product, it is also a critical signal in the respiratory control system. The brain uses carbon dioxide levels to regulate breathing. High carbon dioxide means breathe more. Low carbon dioxide means breathe less. When the sleeping person hyperventilates, they exhale carbon dioxide faster than the body produces it. The carbon dioxide level in the blood drops. The brain interprets this low carbon dioxide as a signal that there is no need to breathe. The respiratory drive shuts off, and so the person stops breathing. They experience an apnea, a complete cessation of breathing. The pause can last 10, 15, sometimes 20 seconds. During this pause, the chest does not move. No air enters or leaves the lungs. The person is, for this brief period, not breathing at all. During the apnea, the oxygen level in the blood begins to fall again. It can drop rapidly from 80% saturation to 70%, then to 60%, then to 50%. At 50% oxygen saturation, the brain is in severe distress. This is a level that would trigger immediate emergency intervention in a hospital. The brain is receiving barely enough oxygen to maintain basic function. The brain, now starved of oxygen, triggers a massive arousal response. This is a primitive survival-level panic. The person jolts awake, their eyes opening, their body tensing. They gasp for air, taking several desperate rapid breaths. The sensation is one of profound suffocation, as if they were drowning or being smothered. The heart pounds. Adrenaline floods the system. It is terrifying. The person takes several large breaths, and their oxygen level begins to recover. It climbs back up to 60%, then 70%, then 75%. The carbon dioxide level also begins to rise as they breathe. The immediate crisis passes. The heart rate slows slightly. The sense of panic eases. The person, exhausted from this surge of adrenaline, begins to calm down. They close their eyes. They drift back towards sleep. And the cycle begins again. This can happen every 3 to 5 minutes all night long. Some climbers experience 10 to 15 apneas per hour. Over an 8-hour night, that is more than 100 episodes of stopped breathing, oxygen desaturation and panicked awakening. It is exhausting. It is terrifying, especially the first time it happens. Many climbers describe it as one of the worst aspects of high-altitude mountaineering. Not the physical exertion, not the cold, but the inability to sleep. The psychological impact of periodic breathing is profound. Sly. It's supposed to be a time of rest, of escape from the demands and dangers of waking life. But at extreme altitude, sleep becomes another source of stress. The person lies in their sleeping bag, dreading the moment when they will stop breathing and jolt awake gasping. Some climbers develop a fear of falling asleep. They try to stay awake, which only increases their exhaustion and impairs their performance the next day. The cognitive effects of this fragmented sleep are severe. Sleep deprivation impairs judgment, slows reaction times, and reduces coordination. Combined with the cognitive impairment caused by hypoxia, the result is a person whose mental function is dramatically compromised. They may appear outwardly functional. They can walk, talk, and follow simple instructions, but their ability to make complex decisions or respond to unexpected situations is severely limited. Research on climbers at extreme altitude has documented measurable changes in brain function. Magnetic resonance imaging studies have shown that prolonged exposure to the death zone causes actual shrinkage of brain tissue, particularly in areas involved in memory and spatial processing. Some of this damage is reversible after descent, but some may be permanent. The combination of hypoxia and sleep deprivation accelerates this damage. For Sherpas, periodic breathing is less severe. Their adapted physiology, the more efficient mitochondria, the higher baseline breathing rate, the wider blood vessels, means their oxygen levels are more steady. They still experience the cycle of hyperventilation, apnea and arousal, but the extremes are less pronounced. The apneas are shorter, typically 8 to 12 seconds rather than 15 to 20. The oxygen drops are less dramatic, perhaps from 75% to down to 65% rather than down to 50%. The arousals are less violent. They wake with a sense of breathlessness, but not with the full-blown panic that many lowland climbers experience. This relative stability means that Sherpas are able to achieve slightly deeper sleep. They spend more time in the lighter stages of sleep and occasionally reach brief periods of deeper sleep. This is still far from restorative, but it is better than the constant cycling wakefulness that lowland climbers endure. This advantage, better sleep at extreme altitude, is one of the reasons Sherpas can work repeatedly at these elevations while maintaining functionality. There is also a difference in how Sherpas and lowlanders perceive and respond to the periodic breathing. For a lowland climber experiencing it for the first time, the sensation of waking gasping for air is novel and frightening. The brain interprets it as a life-threatening emergency which amplifies the stress response. For a Sherpa who has experienced this hundreds of times, the sensation is familiar. It is unpleasant but expected. The brain does not interpret it as a novel threat, so the stress response is more muted. This psychological habituation reduces the overall physiological cost of the experience. He lies in his sleeping bag, eyes closed, breathing irregularly. He's aware of the cold, the pressure of the booties against his feet, the weight of the water bottles at his sides. He's aware of the wind, the flapping of the tent, the presence of his tent mate. He's aware, and then he is not, and then he is again. The transition into sleep is not a descent into darkness. It is more like a flickering. Consciousness dims, then brightens, then dims again. His thoughts become fragmented. He's thinking about the route tomorrow, and then he's thinking about his village, and then he is not thinking at all, and then he's gasping awake, his chest tight, his heart racing. He breathes. He calms. He closes his eyes. The cycle continues. Each time he wakes, there is a moment of disorientation. Where is he? What is happening? Then recognition returns. He is in the tent. He is on the mountain. This is normal. This is what happens here. He breathes. He waits. He drifts again. The quality of this liminal state is difficult to describe. It is not wakefulness. His body is still. His eyes are closed. His mind is not fully engaged. But it's not sleep either. There is no true loss of consciousness, no sustained period of rest. It is something in between, a twilight state where awareness rises and falls like a tide. Time becomes difficult to track. Has he been lying here for 1 hour or 3? He does not know. The darkness is complete, the wind is constant. There are no external markers of time's passage. He drifts in this timeless space suspended between waking and sleeping, between consciousness and oblivion. This is the night at 8,000 meters. This is what sleep means in the death zone. It is not rest. It is not recovery. It is simply a state of reduced demand. A period where the body is not actively working, but is not truly resting either. It is survival, measured in breaths and heartbeats, in the small margin between enough oxygen and not enough. He continues to drift. The liminal state begins. He closes his eyes. His body is exhausted. His muscles ache from the day's work. His lungs are tired from the constant laboured breathing. His mind is fogged by the hypoxia. Every part of him wants to sleep. But sleep does not come easily. At sea level, sleep is a relatively smooth transition. The brain passes through stages of progressively deeper unconsciousness. Light sleep, deep sleep, REM sleep, in a predictable cycle. The body relaxes. The heart rate slows. Breathing becomes regular and shallow. The brain consolidates memories, repairs tissues, and performs the maintenance work that can only happen when we are not awake. But at 8,000 meters, sleep is not like this. The brain, sensing the dangerously low oxygen levels, fights to stay awake. It is terrified of shutting down in an environment where unconsciousness could mean death. This conflict between the body's need for rest and the brain's survival instinct creates a disturbed, fragmented state that is neither fully awake nor fully asleep. The primary manifestation of this conflict is a phenomenon called periodic breathing or Cheney-Stokes respiration. It is a cyclic pattern of breathing that occurs in nearly everyone who sleeps at extreme altitude. The cycle is as follows. First, the person drifts into a light sleep. As they do, their breathing begins to slow and becomes less deliberate. This is normal. During sleep, the body's autonomic nervous system takes over the control of breathing, and the rate and depth of each breath are regulated automatically based on the levels of oxygen and carbon dioxide in the blood. But at high altitude, the oxygen levels are already dangerously low. As the breathing slows, the oxygen level in the blood drops even further. After a few breaths, the brain's oxygen sensors detect this drop. They send a signal. Breathe more. The sleeping person's breathing suddenly becomes rapid and deep. They hyperventilate, taking in as much air as possible. This rapid breathing raises the oxygen level in the blood, but it also lowers the carbon dioxide level. Carbon dioxide is not just a waste product, it is also a signal. The brain uses carbon dioxide levels to regulate breathing. High carbon dioxide means breathe more. Low carbon dioxide means breathe less. When the sleeping person hyperventilates, they blow off too much carbon dioxide. The brain interprets this as a signal to stop breathing, and so the person stops. They experience an apnea, a complete cessation of breathing. The pause can last 10, 15, sometimes 20 seconds. During this pause, the oxygen level in the blood plummets. It can drop from 90% saturation to 70% or lower in a matter of seconds. The brain, now starved of oxygen, panics. It triggers a massive arousal response. The person jolts awake, gasping for air, their heart pounding, a profound sense of suffocation flooding their consciousness. They take several desperate, rapid breaths, and their oxygen level begins to recover. As they calm down, they drift back towards sleep, and the cycle begins again. This can happen every few minutes, all night long. Some climbers experience dozens of apneas per hour. The result is that they never achieve deep sleep. They spend the entire night oscillating between light sleep and panicked waking. It is exhausting. It is terrifying, especially the first time it happens. Many climbers describe it as one of the worst aspects of high-altitude mountaineering. Not the physical exertion, not the cold, but the inability to sleep. For Sherpas, periodic breathing is less severe. Their adapted physiology, the more efficient mitochondria, the higher baseline breathing rate, the wider blood vessels, means their oxygen levels are more stable. They still experience periodic breathing, but the apneas are shorter, the oxygen drops are less dramatic, and the arousals are less violent. They are able to achieve slightly deeper sleep, and they spend more of the night actually resting rather than gasping awake. But even for Sherpas, sleep at 8,000 meters is not restorative. It is a strange liminal state, a twilight between waking and sleeping, where consciousness is reduced but never fully extinguished. It is not the sleep of home, where you close your eyes in the evening and wake hours later feeling rested. It is a fragmented, hallucinatory drift, punctuated by moments of clarity and fear. He lies in his sleeping bag, eyes closed, breathing irregularly. He is aware of the cold, the pressure of the booties against his feet, the weight of the water bottles at his sides. He is aware of the wind, the flapping of the tent, the presence of his tent mate. He's aware, and then he is not, and then he is again. He drifts, the small mercy of oxygen. After perhaps 20 minutes of this broken, unsettling half-sleep, he reaches out of his sleeping bag. His hand finds the oxygen cylinder that is lying next to him. It is a small medical-grade cylinder, made of aluminum, containing compressed oxygen at high pressure. The cylinder is cold to the touch. Everything at this altitude is cold, but the metal has a reassuring solidity. It is one of the most important pieces of equipment on the mountain, and its presence beside him is a small comfort. The cylinder is surprisingly heavy for its size, weighing several kilograms even when partially depleted. Inside, oxygen has been pressurized to roughly 200 times atmospheric pressure at sea level. This compression allows a large volume of oxygen to be stored in a relatively small space. A typical climbing cylinder holds about 2 liters of physical volume, but when the gas is released and allowed to expand to normal pressure, it yields hundreds of liters of breathable oxygen. Attached to the top of the cylinder is a regulator, a mechanical valve that controls the flow of oxygen from the high-pressure environment inside the cylinder to the low-pressure environment outside. The regulator is a precision instrument designed to deliver a steady, controlled flow regardless of how much pressure remains in the cylinder. It has a dial or lever that allows the user to adjust the flow rate measured in liters per minute. He adjusts the regulator to a flow rate of 1 liter per minute. This is a very low flow rate. At sea level, at rest, an average adult breathes about 6 liters of air per minute. At 8,000 meters, the breathing rate is much higher, perhaps 30 to 40 breaths per minute, and the total volume of air moved through the lungs might be 15 to 20 liters per minute. 1 liter per minute of pure oxygen, mixed with 15 to 20 liters per minute of ambient air, does not dramatically change the overall oxygen concentration. At 8,000 meters, the air still contains 21% oxygen, but because the atmospheric pressure is only 1/3 of sea level pressure, each breath contains only 1/3 as many oxygen molecules. When you add 1 liter per minute of pure oxygen to the breathing mixture, the net effect is roughly equivalent to reducing the perceived altitude by about 1,500 meters. Instead of feeling like you are at 8,000 meters, it feels more like you are at 6,500 meters. This is still extraordinarily high, but it is a significant improvement. Climbers often use 4 to 6 liters per minute while moving and working, which makes exertion somewhat less difficult. But oxygen cylinders are heavy, and the supply is limited. A cylinder that might last 8 to 10 hours at 1 liter per minute will last only 2 to 3 hours at 4 liters per minute. For sleeping, 1 to 2 liters per minute is typical. The goal is not to make the air feel normal. That would deplete the supply too quickly. The goal is simply to reduce the severity of the hypoxia enough to allow some semblance of rest. The mask is a simple, lightweight device made of rubber or silicone. It covers the nose and mouth and is held in place by an elastic strap that goes around the head. The mask has a soft, flexible edge that conforms to the contours of the face, creating a seal that prevents oxygen from escaping. Inside the mask is a small reservoir, a flexible bag that fills with oxygen from the regulator, With each inhalation, the climber draws air from this reservoir, mixing it with ambient air that enters through small vents in the mask. The design of these masks represents decades of engineering refinement. Early oxygen masks used in the first attempts to climb Everest in the 1920s and 30s were crude, uncomfortable, and prone to freezing. The valves would ice up from the moisture in exhaled breath. The masks would frost over, blocking airflow. The rubber would become stiff and brittle in the cold. Modern masks have overcome most of these problems through better materials and design, though ice formation remains an issue, particularly on long summit days. He places the mask over his face, adjusting the strap to hold it firmly into place. The mask covers his nose and mouth, leaving his eyes exposed. The soft edges press against his cheeks, his upper lip, the bridge of his nose. The sensation is slightly claustrophobic at first, but it becomes familiar quickly. The oxygen flows from the cylinder through a thin plastic tube into the mask. With each breath, he inhales a mixture of the ambient air and the supplemental oxygen. The effect is subtle but significant. The oxygen does not make him feel energized or alert. There is no rush of clarity or strength, but the periodic breathing becomes less severe. The apneas are shorter, perhaps 8 to 10 seconds instead of 15 to 20. The drops in blood oxygen saturation are less dramatic. Instead of his oxygen level plummeting from 75% to 50% during an apnea, it might drop only to 60 or 65%. This is still dangerously low, but it is not as catastrophic. The brain's panic response is slightly calmed. When the oxygen level drops to 65% instead of 50%, the arousal is less violent. He still wakes, still feels the breathlessness, but the sense of suffocation is less intense. The adrenaline surge is smaller. His heart rate does not spike as dramatically. He is able to drift into a slightly deeper state of rest, though it is still far from true sleep. The brain is exquisitely sensitive to oxygen deprivation. It represents only about 2% of body weight, but it consumes roughly 20% of the body's oxygen supply. Unlike muscles, which can function anaerobically for short periods, the brain has almost no capacity for anaerobic metabolism. It requires a constant, uninterrupted supply of oxygen to maintain function. At normal sea level oxygen saturation, 95 to 100%, the brain operates at full capacity. At 85%, cognitive function begins to decline measurably. At 70%, the brain is in distress. At 60%, consciousness becomes difficult to maintain. Below 50%, most people will lose consciousness entirely. When a climber's oxygen saturation drops to 50% during an apnea, the brain is on the edge of shutdown. By keeping the oxygen saturation from dropping below 60 or 65%, the supplemental oxygen prevents the brain from reaching that critical threshold. There is another benefit to the supplemental oxygen, one that is often overlooked but is equally important. Oxygen is required for metabolism. The body generates heat by burning fuel, fats, carbohydrates, proteins, and this combustion requires oxygen. At 8,000 meters, with only one-third the available oxygen, the body's metabolic furnace is running on a lean mixture. It is not producing as much heat as it could. Cellular respiration, the process by which cells convert glucose and oxygen into energy, is a controlled form of combustion. When oxygen is abundant, the glucose is completely oxidized, broken down all the way to carbon dioxide and water, and the maximum amount of energy is released. When oxygen is scarce, the glucose can only be partially broken down. The process stops at an intermediate stage, producing lactic acid instead of carbon dioxide. Less energy is released, and less heat is generated. At extreme altitude, the body's cells are operating in a state of chronic oxygen scarcity. They are burning fuel inefficiently, producing less heat than they would at sea level. This is one of the reasons climbers feel so cold at altitude, even when they are well insulated. It is not just that the outside air is cold, it is that the body's internal heat generation is impaired. The supplemental oxygen, by providing more fuel for the metabolic fire, allows the body to burn slightly hotter. The internal temperature rises by a degree or 2 Celsius. This small increase in core warmth is enough to make a significant difference. The extremities, the hands and feet, receive slightly more warm blood. The risk of frostbite is reduced. Studies of climbers using supplemental oxygen have shown that skin temperature, particularly in the extremities, is several degrees higher than in climbers not using oxygen at the same altitude. The psychological effect of using oxygen is also significant. At extreme altitude, the constant sensation of oxygen starvation, the air hunger, the feeling that you can never quite catch your breath, is profoundly stressful. It creates a background level of anxiety that never entirely goes away. The body is sending constant distress signals to the brain. Not enough air, not enough oxygen, danger. These signals are exhausting and contribute to the overall sense of being in crisis. When supplemental oxygen is used, these distress signals are reduced. The body is still oxygen deprived, but it is not in quite as much distress. The constant sense of suffocation eases slightly. This reduction in psychological stress has physiological benefits. The body produces less cortisol and adrenaline, the stress hormones that increase heart rate and elevate blood pressure. Lower stress hormone levels mean the body can allocate more resources to basic maintenance and repair rather than burning everything in a constant state of emergency response. For Sherpas, the decision to use oxygen for sleep is pragmatic. Their adapted physiology means they function better at altitude than lowlanders, but they are not immune to the effects of extreme hypoxia. They still experience periodic breathing, cognitive impairment and metabolic stress. Supplemental oxygen reduces all of these, allowing them to achieve better rest and maintain better function over the course of a multi-day climb. Some Sherpas have climbed Everest without using any supplemental oxygen, a feat that requires exceptional physiological adaptation and enormous mental toughness. But for sleeping at high camps, even the most elite Sherpas typically use oxygen. The benefits are too significant to forego. The oxygen cylinder beside him represents a finite resource. Each litre of oxygen consumed is a litre that is no longer available for later use. The expedition has brought a limited number of cylinders up the mountain and they must be allocated carefully. Some cylinders are reserved for the summit push, when the climbing is most strenuous and the altitude is highest. Some are kept in reserve for emergencies. The cylinders used for sleeping at high camps are factored into this overall budget, but they cannot be used wastefully. He knows that the cylinder he is breathing from now will be depleted by morning. At 1 litre per minute, then, over 8 hours, he will consume roughly 480 litres of oxygen in its expanded state. This represents most or all of the capacity of a standard climbing cylinder. In the morning, he will switch to a fresh cylinder for the day's work, and the depleted cylinder will be left at the camp, perhaps to be retrieved later, perhaps to remain on the mountain as one of the thousands of pieces of equipment that accumulate at the high camps over the decades of expeditions. He breathes through the mask, each breath bringing a small, measured flow of oxygen into his lungs. The hiss of the regulator is a soft, rhythmic sound, quieter than the roar of the stove but still audible over the wind. It is a mechanical sound, a reminder of the technology that is keeping him alive. Without this cylinder, without this flow of compressed gas, the night would be much harder, perhaps impossible. He continues to drift in and out of sleep, but the quality of the drift has improved. The panic is less, the gasping is less frequent and less violent. The night becomes slightly more tolerable. The oxygen is not a miracle. It does not transform the death zone into a habitable place, but it makes the uninhabitable slightly less so. It provides a small margin, a buffer, a mercy. And in a place where margins are measured in single-digit percentages of blood oxygen saturation, this small mercy can be the difference between survival and failure, between waking to see the dawn and not waking at all. He breathes. The oxygen flows. The night continues. He rests in his own particular way in this strange twilight between waking and sleeping, sustained by technology and biology and will, enduring through the long hours until the sun returns. The calm resilience. There is a particular quality to the Sherpa approach to this experience that is difficult to describe, but essential to understand. It is not toughness, exactly, though Sherpas are certainly tough. It is not stoicism, though they endure hardship without complaint. It is something more subtle, a calm, patient acceptance of the situation as it is. In Western mountaineering culture, there is often a language of battle and conquest. The mountain is described as an adversary to be defeated. The climb is a struggle, a fight. The climber attacks the summit, conquers the peak. This framing is dramatic and compelling, but it also creates a certain mindset, or one of opposition. of constant tension between the climber and the environment. Sherpas do not typically use this language. For them, the mountain is not an enemy. It is a place where they work. It is difficult, dangerous, unforgiving, but it is not malevolent. It simply is. The cold is cold, the altitude is high, the wind blows. These are facts, not challenges. You do not fight them. You accommodate them. This perspective is not resignation. It is not a passive acceptance of fate. It is an active, engaged calmness. You must melt the snow, so you melt the snow. You must eat, even though you are not hungry, so you eat. You must rest, even though sleep is fragmented and unpleasant, so you rest. Each task is approached methodically, without drama, without wasted energy on frustration or fear. This calm resilience is partly cultural and partly practical. Panic is expensive. The body's stress response, the surge of adrenaline, the elevated heart rate, the flood of cortisol consumes energy and oxygen that the body cannot afford to waste. A climber who is constantly tense, constantly on edge, will burn through their reserves much faster than a climber who remains calm. At extreme altitude, where energy is already scarce, this difference can be life or death. The Sherpas' calmness is also a product of experience. For many of them, this is not their first time at 8,000 meters. It is not even their second or third. It is their 10th, their 20th, their 50th. They have spent more nights in the death zone than most Western climbers will spend in their entire lives. They know what to expect. They know that the sleep will be bad, that they will wake gasping, that they will be cold and uncomfortable. This knowledge removes the element of surprise. There is no panic because there is no novelty. It is simply what happens. This is not to say that Sherpas do not feel fear or discomfort. They do. They are human. But they do not allow these feelings to dominate their behaviour. They acknowledge the fear, note the discomfort, and continue with the task at hand. This is a kind of mental discipline, cultivated over years of work in extreme environments. There is also a social dimension to this resilience. Sherpas grow up in a culture where high-altitude work is normalised. Their fathers, uncles, brothers, and cousins are climbers. They hear stories of expeditions from a young age. The work is dangerous, and everyone knows people who have died on the mountain. But it is also a source of pride and income. It is how many Sherpa families survive. This cultural context provides a framework for understanding the hardship. It is not senseless suffering. It is work, honourable and necessary. In the sleeping bag, he does not struggle against the periodic breathing. He does not curse the cold or the altitude. He simply breathes, drifts, wakes, breathes again. The night is long, but it will end. The summit push will come, or the descent will begin, and this will all become memory. For now, there is only the present moment, the cold, the thin air, the fragile tent, the presence of his partner, the small mercy of the oxygen flowing into his lungs. He continues to rest, in his own particular way. The Mother Goddess. In the half-sleep, his mind wanders. Thoughts are slow and fragmented, images drifting across the consciousness like clouds. He thinks of home, of the village in the Khumbu Valley, of his family. He thinks of the work ahead, tomorrow's climb, the loads to be carried, the route to be fixed. He thinks of the mountain. The mountain is Chomolungma. This is her name in Tibetan, the language of the Sherpas. It means Mother Goddess of the World. The Nepali name is Sagamatha, Goddess of the Sky. The English name, Everest, is a colonial imposition named after George Everest, Eard, a British surveyor general of India who never saw the mountain in person and who, reportedly, objected to having his name attached to it. To the Sherpas, the mountain is Chomolungma, and she is sacred. This is not metaphor. The mountain is not like a goddess. She is a goddess, a living skirsiskam, a living presence, a being deserving of respect and reverence. This belief is central to Sherpa culture and to Tibetan Buddhism more broadly. The natural world is not separate from the spiritual world. Mountains, rivers, forests, and lakes are inhabited by spirits and deities. These beings have agency, preferences, and the power to help or harm. To climb the mountain is to enter her domain, and this cannot be done without permission. This worldview is fundamentally different from the perspective that dominates much of Western mountaineering culture. In the Western tradition, particularly since the 18th and 19th centuries, mountains have been viewed as objects to be measured, understood, and ultimately conquered. The language of mountaineering reflects this. Climbers attack the summit. They conquer the peak. They defeat the mountain. The mountain is an adversary, a challenge to be overcome through skill, strength, and determination. Victory is reaching the top. Is turning back. The Sherpa perspective contains no such opposition. Chomolungma is not an adversary. She is not hostile, nor is she neutral. She is a presence, powerful, ancient, who allows or denies passage according to her will. The climber does not conquer her. The climber asks for her blessing, approaches with humility, and accepts whatever outcome she determines. Success is not victory over the mountain, but rather a gift from the mountain, a temporary permission granted by a being far greater than any human. This belief shapes every aspect of how Sherpas approach the work of climbing. It begins long before anyone sets foot on the mountain itself. Every expedition that departs from base camp, without exception, begins with a puja ceremony. A puja is a Buddhist ritual of offering and blessing. It is not performed as a courtesy to Sherpa cultural sensibilities, nor is it done for the benefit of tourists seeking an authentic experience. It is a genuine spiritual practice, deeply felt and taken seriously by the Sherpas, and increasingly by many Western climbers who have come to understand its significance. The ceremony requires preparation. A lama, a Buddhist monk or spiritual teacher, must be brought to base camp. This is not always simple. Base camp sits at 5,364 meters, an elevation where even walking is difficult for those unaccustomed to altitude. The lama must make the journey up from one of the lower villages, typically Tengboche, where the most significant monastery in the Khumbu region is located. The journey takes several days. The lama is usually accompanied by 1 or 2 junior monks who assist with the ceremony. At base camp, a site for the altar is chosen. This is typically a prominent elevated spot with a clear view of the mountain. The altar itself is built from stones gathered from the surrounding area. The stones are carefully stacked to create a stable platform, roughly waist-high and wide enough to hold the various offerings. The construction of this altar is itself a meditative act, performed with care and intention. Once the altar is complete, it is prepared for the ceremony. A tall pole is erected at the centre or at the back of the altar. This pole, often a stripped tree branch or a length of bamboo, will serve as the anchor point for the prayer flags. The surface of the altar is covered with juniper branches, which will be burned during the ceremony. Juniper smoke is considered purifying in Tibetan Buddhist practice, capable of cleansing both physical objects and spiritual impurities. The offerings are then arranged on the altar. These vary depending on what is available and what the lama specifies, but they typically include rice, which symbolizes abundance and sustenance, fresh fruit when it can be obtained at this elevation, representing the bounty of the earth, torma, small sculptures made from barley flour and butter, often painted in bright colours, which serve as symbolic offerings to the deities, incense, which will be burned throughout the ceremony, and sometimes small amounts of alcohol, usually beer or rice wine, offered in cups. In addition to these traditional offerings, the climbing equipment itself is brought to the altar. Ropes, harnesses, ice axes, crampons, helmets, all the tools that will be used on the mountain, are laid out near the altar, or hung on lines strung nearby. These items will be blessed during the ceremony, purified by the juniper smoke and consecrated for safe use. The ceremony typically begins in the early morning, when the air is still and the mountain is most visible. The expedition members, Sherpas and foreign climbers alike, gather around the altar. They sit on the ground or on stones, forming a semicircle facing the altar and the mountain beyond. The atmosphere is quiet, contemplative. Even climbers who do not share the Buddhist faith participate respectfully, understanding that this ceremony is important to their Sherpa colleagues and increasingly recognizing its value as a moment of reflection before undertaking a dangerous endeavour. The lama begins by lighting the juniper branches on the altar. The wood catches slowly, releasing thick, white, aromatic smoke that rises into the still air. The scent is distinctive, sharp, resinous, cleansing. The smoke is fanned across the climbing equipment, bathed over the ropes and axes, the crampons and harnesses. Each piece of gear is passed through the smoke, turned in the cleansing cloud, blessed. The lama then begins to chant. The chants are in Tibetan, ancient prayers and mantras that have been passed down through generations. Most of the listeners do not understand the words, even many Sherpas, whose daily language is a related but distinct dialect, do not speak liturgical Tibetan fluently. But the sound itself is powerful, the lama's voice is deep, resonant, rhythmic, the chants follow complex melodic patterns, sometimes rising to a sustained high note, sometimes falling to a low rumble that seems to vibrate in the air. The mantras are repetitive, cyclical. The most common is Om Mani Padme Hum, the 6-syllable mantra associated with Avalokiteshvara, the Bodhisattva of compassion. This mantra is central to Tibetan Buddhism, repeated millions of times throughout a practitioner's life. It is carved on stones, printed on flags, spun in prayer wheels, and spoken as a constant meditative practice. During the puja, it is chanted dozens or hundreds of times, the syllables blending into a continuous flow of sound. As the chanting continues, prayer flags are strung. These flags are a defining feature of the Himalayan landscape, visible in every Sherpa village, along every trail, at every pass and summit. The flags are rectangular pieces of cotton cloth printed with woodblock images and texts. The images typically depict the wind horse, a mythical creature that carries prayers across the sky, surrounded by mantras and sacred symbols. The texts are prayers for peace, compassion, and protection. The flags come in 5 colours, which must be arranged in a specific order: blue, white, red, green, and yellow. These colours represent the 5 elements: sky, air, fire, water, and earth, which in Tibetan cosmology make up the universe and the human body. The proper sequence is important. The flags are strung on long ropes, often dozens of flags per rope. And these ropes radiate outward from the altar in all directions, creating a web of colour and prayer that extends across the camp. The act of hanging the prayer flags is itself a prayer. The flags are not merely decorative, they are functional religious objects. As the wind blows through them, it is believed to carry the prayers printed on the cloth outward into the world. The wind becomes a vehicle for blessing. Each flutter of the flag, each gust that sets them snapping, is a prayer sent forth. Over time, the flags fade, bleached by the intense ultraviolet light of high altitude and shredded by the constant wind. This fading is not seen as deterioration, but as the completion of the flag's purpose. The prayers have been fully released into the world. New flags will be hung when needed. At base camp during a puja ceremony, the prayer flags are strung in lines that extend up toward the mountain itself, as far as the terrain allows. The visual effect is striking, bright colours against the grey rock and white ice, a human assertion of hope and reverence in an indifferent landscape. The sound is equally distinctive. Dozens or hundreds of flags, snapping and fluttering in the wind, create a constant rustling that becomes part of the auditory environment of base camp. It is a sound that says, "We are here, we have asked permission, we have made our offerings." As the chanting and the flag stringing continue, food is prepared. This will be shared at the conclusion of the ceremony, a communal meal that symbolises the unity of the expedition. The food is simple: tea, rice, perhaps some bread or biscuits, but it is blessed by its association with the ceremony. Eating together, after the prayers and offerings, creates a bond among the participants. They are no longer simply individuals who happen to be on the same expedition. They are a community, united by the blessing they have received and by their shared intention to climb the mountain respectfully. The Lama may also give a teaching during the ceremony. This is not a long sermon, but rather a brief reflection on the nature of the undertaking, the importance of approaching the mountain with the right motivation, and the need for compassion and cooperation among the climbers. The specific content varies depending on the Lama and the circumstances, but the underlying message is consistent. The mountain is greater than you, approach with humility, take care of each other. Toward the end of the ceremony, the Lama gives individual blessings to each person present. They come forward one at a time, bowing their heads. The Lama may touch their foreheads with a sacred object, a small statue, a ritual implement, or simply his hand while reciting a short prayer. He may tie a red or white string around their necks. These strings, called sungdi, are protective amulets. They are blessed during the ceremony and are believed to carry the Lama's blessing and the mountain's permission. Many climbers wear these strings for the entire duration of the expedition, removing them only after they have descended safely. The blessing is a moment of personal connection. The Lama looks at each person, meets their eyes, offers the blessing directly and individually. For the Sherpas, this is a moment of profound significance. They have received the blessing of a respected spiritual teacher and, through him, the provisional permission of Chomolungma herself. For Western climbers, even those who do not believe in the religious framework, the moment often carries unexpected emotional weight. There is something powerful about being looked at with genuine compassion and wished well before undertaking something dangerous. The ceremony concludes with a final offering of the Torma sculptures. These are burned in the juniper fire, sending their essence upward with the smoke. More incense is added. The Lama may ring a bell or blow a ceremonial horn marking the completion of the ritual. The fire is allowed to burn down. The participants sit for a while longer, drinking tea, eating the blessed food, talking quietly. The puja is not a guarantee of safety. Sherpas know this. Chomolungma grants permission, but she does not remove danger. The mountain remains a place of objective hazards, avalanches, rockfall, storms, altitude sickness, that can kill the blessed as easily as the unblessed. The puja is not magical protection. It is rather a spiritual framework that accomplishes several things. First, it establishes the correct relationship between the climbers and the mountain. The climbers are guests, supplicants. They have asked permission, made offerings, shown respect. This mindset of humility rather than hubris has practical benefits. Humble climbers are cautious climbers. They pay attention to conditions. They listen to warnings. They are willing to turn back if the mountain indicates, through weather or hazard, that passage is not granted today. Arrogant climbers, by contrast, push on regardless of conditions, confident in their own abilities, and this confidence kills. Second, the puja creates a sense of community and shared purpose among the expedition members. They have participated together in something meaningful. This shared experience builds trust and cooperation, which are essential for safety on the mountain. Climbing at extreme altitude is not an individual sport. It requires teamwork, communication, and mutual support. The puja initiates this process. Third, the puja provides psychological grounding. Climbing into the death zone is terrifying, even for experienced Sherpas. The knowledge that you have been blessed, that you have performed the correct rituals, that you have approached with respect, this knowledge provides a measure of comfort. It does not eliminate fear, but it contextualizes it. The suffering of the climb is not meaningless. It is part of a larger spiritual journey, undertaken with the mountain's provisional blessing. For Sherpas, this spiritual framework is not separate from the physical and technical aspects of climbing. It is integrated with them. Checking your oxygen regulator and offering prayers are both part of the same process, preparing yourself physically and spiritually for the work ahead. There is no contradiction between using modern climbing technology and honouring the mountain as a goddess. The ropes, the oxygen bottles, the radios, these are tools that Chomolungma has allowed humans to develop and use. They are part of how humans can safely move through her domain. In the tent, drifting into the half-sleep, he recalls the puja ceremony from weeks ago at base camp. He remembers the smell of juniper smoke, the sound of the Lama's chanting, the sight of the prayer flags strung out toward the mountain. He remembers receiving the blessing, the cool touch of the Lama's hand on his forehead, the weight of the protection string around his neck. He is still wearing that string now, beneath his base layer against his skin. He thinks of the prayer flags still strung at base camp and at the lower camps, fluttering in the wind even now, even in this darkness, sending their prayers into the night. He thinks of the mantra Om Mani Padme Hum. He may not recite it consciously, he is too tired, too hypoxic, but it is there in his mind, a rhythm beneath the rhythm of his breathing. Chomolungma is all around him. He is inside her. The tent sits on her shoulder. The ice beneath him is her body. The wind that batters the tent is her breath. She is not hostile. She is not kind. She is simply present, immense, indifferent in the way that gods are indifferent. Not cruel, but operating on a scale and timeline that makes individual human lives insignificant. He has asked her permission, and she has not refused him. He is here. He is still alive. That is the provisional answer. But permission can be withdrawn at any moment. A storm, an avalanche, a sudden failure of his body's systems, He knows this. Every Sherpa knows this. The mountain gives and the mountain takes away. This knowledge, rather than creating despair, creates a kind of peace. He's not trying to conquer Chomolungma. He's not trying to prove anything. He's simply doing his work. The work his father did. The work his uncles and cousins do. The work that feeds his family. He approaches this work with respect and care, and he accepts that the outcome is not entirely in his control. This acceptance is not fatalism. He will still do everything he can to be safe. Check his gear, watch the weather, listen to his body, make good decisions. But beneath all the technical competence, beneath all the careful preparation, there is this. He is in the hands of Chomolungma, and he trusts that if he is approached correctly with humility and respect, she will protect him as much as her nature allows. This spiritual framework transforms the experience. The cold is not just suffering, it is part of being in the goddess's presence. The thin air is not just deprivation, it is the atmosphere of the sacred. The fear is not just fear, it is awe, the appropriate emotion when confronted with something infinitely greater than yourself. Western climbers, even those who do not share the Buddhist faith, often come to understand something of this perspective after spending time with Sherpas on the mountain. They may not believe in Chomolungma as a literal goddess, but they come to recognize that approaching the mountain with humility and respect, rather than with an attitude of conquest, is not just spiritually appropriate, but practically safer. The mountain does not care about your ego. The mountain does not reward arrogance. The mountain simply is, and those who approach with humility tend to make better decisions and survive longer. The Sherpas have known this for 500 years. It is embedded in their culture, passed from generation to generation, reinforced by the stories of those who returned and those who did not. The mountain is not to be conquered. The mountain is to be respected, approached carefully, and left when she indicates it is time to leave. In the sleeping bag, in the darkness, in the strange half-world between waking and sleep, he rests in this understanding. He is small. The mountain is vast. He has done what he can. He has prepared his body, his gear, his mind. He has received the blessing. He is approached with respect. Now he simply endures, breath by breath, through the long night, trusting that Chomolungma will allow him to see the dawn. The wind continues to roar. The cold continues to press against the thin walls of the tent. But inside there is this, a human life sustained by technology and biology and community, and perhaps by the provisional blessing of the Mother Goddess of the world. He breathes, he drifts, he waits. The night continues, and he continues within it, small but persistent, a brief warmth in an infinite cold, a guest in a sacred place. The deep middle hours. It is now deep into the night. The exact time is difficult to know. He has a watch, but looking at it requires effort. He would have to free his arm from the sleeping bag, turn on his headlamp, and focus his eyes on the small glowing numbers. This feels like too much work for information that does not change his situation. It is night. That is enough. The wind has not lessened. If anything, it seems louder now. Or perhaps he is simply more aware of it in the absence of other distractions. The tent fabric drums and snaps, a constant percussion. Occasionally there is a particularly strong gust and the entire tent frame bends and flexes. The aluminum poles are designed to do this, to bend rather than break, but each time it happens, there is a moment of anxiety. Will the tent hold? So far it always has. He has slept in his own particular way. The periodic breathing has continued, but the oxygen has helped. He has drifted into light sleep perhaps a dozen times, each episode lasting a few minutes before the apnea and the gasping wake him. But the apneas are short, 10 seconds rather than 20, and the panic is muted. It is unpleasant, but it is manageable. His body is consolidating what resources it can. The muscles are not healing. That requires more oxygen and better circulation than is available here, but they are at least resting. The metabolic processes are minimal, but they are ongoing. The heart is still beating, the lungs still breathing. The small internal furnace continues to produce heat, and that heat, trapped by the sleeping bag and the layers of clothing, is keeping him alive. He is thirsty. This is a constant state at altitude. He reaches for one of the water bottles inside the sleeping bag. It is still liquid, though barely. The water is ice cold, almost painful to drink. He forces himself to take several long swallows, feeling the cold liquid travel down his throat and into his stomach. It is deeply unpleasant, but necessary. Dehydration is one of the many silent threats here, and he knows he must drink even when he does not feel thirsty. His tent mate is also awake, or perhaps in a similar state of half-sleep. There is a rustling from the other sleeping bag, a cough, the sound of breathing that is irregular and laboured. Neither of them speaks. There is nothing to say, they are both simply enduring. He thinks about the morning. In a few hours, the sun will rise, the temperature will begin to climb, though not by much. Perhaps it will reach negative 20 degrees during the day. They will melt more snow, eat another meal, prepare their gear. Then they will either continue up the mountain toward the summit, or they will descend, depending on the weather and the condition of the route. This decision has not yet been made. It will be made in the morning, after consultation with the climbing leader and the other Sherpas. But that is the future. For now, there is only the present. The cold, the wind, the thin air, the fragile tent, the sleeping bag, the oxygen mask, the sound of breathing, the presence of another human. He is aware of all these things, but he does not dwell on them. He simply accepts them. This is the situation. This is where he is. The night continues. It is not infinite, though it feels that way. The sun will rise, it always does. Until then, he waits, the persistence of rest. The term rest is perhaps misleading. What is happening in this tent, in this sleeping bag, is not the kind of rest we think of when we imagine a good night's sleep. It is not restorative. The body is not being repaired. The mind is not being refreshed. In many ways, the climber is worse off in the morning than he was in the evening, more dehydrated, more exhausted, more depleted, and yet it is rest. It is the best rest that is possible in this environment. The body is not moving. The metabolic demand has dropped from the extreme levels of daytime exertion to the slightly less extreme levels of nighttime basal metabolism. The mind, though not truly sleeping, is at least not required to make decisions or solve problems. This reduction in demand, however small, is valuable. It is the difference between being able to continue tomorrow and being unable to continue. This is what survival at extreme altitude looks like. It is not heroic in the conventional sense. It is not dramatic. It is simply a long, methodical process of managing resources, reducing demands, and enduring. The Sherpa in his sleeping bag is not conquering anything. He is not defeating the mountain. He is simply outlasting the night. The sleeping bag holds. It is rated to negative 40 degrees Celsius, and the temperature inside the tent is colder than that, but the bag is working. The down is lofted, trapping air, slowing the loss of heat from his body. He is cold, certainly, but he is not freezing. His core temperature is stable. His extremities, fingers and toes, are cool but not frostbitten. The bag is doing its job, the tent holds. The wind is ferocious, gusting well over 100 miles per hour at times, but the geodesic dome design is effective. The lattice of aluminum poles distributes the wind load across the entire structure. No single point bears too much stress. The nylon fabric is taut aerodynamic. The tent bends and flexes, but it does not break. It has been engineered for exactly this purpose, and it is fulfilling that purpose. The oxygen holds, the cylinder still has gas. The regulator is functioning, the mask is in place, the flow rate is steady at 1 litre per minute. This small, constant supply of oxygen is making the night tolerable. Without it, the periodic breathing would be much worse, the apneas longer, the panic more severe. With it, he can drift into something approaching sleep, however fragmented. The body holds. His Sherpa physiology, honed over 5 centuries of high-altitude life, is keeping him alive. His mitochondria are extracting energy from the limited oxygen available. His blood is thin and flowing freely, delivering what oxygen there is to his tissues. His breathing rate is elevated but stable. His heart is working hard but not in crisis. This is what his ancestors' bodies were selected for. This is what his body is designed to do. The partnership holds. His tent mate is nearby, breathing, present. They are sharing this experience, sharing the space, sharing the burden. If something goes wrong, they will help each other. This is understood without being spoken. It is the foundation of their work. The spiritual framework holds. The mountain is Chomolungma, the mother, goddess. She has granted permission for this climb provisionally through the puja ceremony and the blessings of the Lama. The Sherpa has approached with respect, and he continues to approach with respect. This belief provides context and meaning. It makes the suffering tolerable, not because it eliminates the suffering, but because it places the suffering within a larger story. All of these layers, material, biological, social, spiritual, are working together. No single layer is sufficient. Remove any one of them, and survival becomes much more difficult, perhaps impossible. But together, they create a system that allows a human being to rest, however briefly and inadequately, in a place where human life should not be possible. The night is not over yet. There are still hours until dawn, but the worst is past. The coldest part of the night is typically the hour before sunrise, and that hour is approaching. After that, the temperature will begin to rise, the sun will return, the day will begin with all its demands and dangers, but that is not yet. For now, in the deep middle of the night, 2 men rest at 8,000 meters. They are cold, exhausted, uncomfortable, and in a state of constant low-level physiological crisis. But they are alive, they are resting, and that, in this place, is enough. The wind continues to scream, the tent continues to shake, the mountain continues to breathe, and inside the small, fragile bubble of warmth, 2 human lives persist. Thank you for listening. Rest well.